Welcome to the stream. Strap your seatbelt. This is going to be a long one, even by this channel standard. So today we're going to be doing some complex analysis, and the main text we'll be following is Brown and Churchill, which is a classic text, and it's currently in its 9th edition. And don't worry if you don't have the latest edition, older edition is fine. So the complex analysis is how do we put this? So on this channel, we mostly focus on applied mathematics, right? And complex variables is one of those things that don't scream immediate applications, right? So for example, most of the stuff we do on the channel, like probability and statistics, stochastic process, and differential equation, that kind of thing, has immediate application. You model things with them. Complex variable is a little bit subtle. Typically, as far, unless for, so to say, actually, you know what? I'm losing my mind right now. Sorry, guys. I was just saying that the subject of complex analysis don't scream immediate application, unlike many of the applied math subject. Right? But the thing is, the moment you enter into deeper territory, the blue water of applied mathematics, complex variables shows up everywhere. It's just the reality. Okay, it's kind of miraculous, but this is the way it is. So, for example, if we covered some of the transforms yesterday, well, like Z transform, Laplace transform, Fourier transform, even the simplest transform, like the Z transform, requires complex analysis to be fully understood. The intuitive idea of transform has nothing to do with complex variables per se, but to really understand it, to calculate stuff with it, to prove theorems, you cannot live without complex variables. Complex variables is what integral transform breathes. You can put it that way. And also, complex variables has connections with so many different branches of mathematics. It's almost like a glue that connects all seemingly disconnected fields together. Like even in pure mathematics, this is the case. Like who would have thought, right, that number theory, the study of integers, would require complex numbers? Fermat's last theorem was proved using techniques from analytic number theory, which is essentially using complex variables to study integers. How miraculous is that? Okay, so this is the thing. So don't be discouraged if you don't see any immediate application right away, because just like real analysis, studying it right away may feel a little bit dry, a little bit boring, but they will pay off immensely. Okay, and this is in fact how analysis historically was developed. You solve complicated problems, basically. As soon as you enter the blue water of applied mathematics or pure mathematics, complex variable shows up everywhere. All right, so without further ado, let's get started. So here, let's start with complex numbers. This is section 1. Complex numbers, sum and product. Chapter 1, complex numbers. Sum and product. So we're defining algebraic operations for complex numbers. Okay, there you go. So first let's draw a diagram. This is x-axis, y-axis. Complex numbers can be defined as ordered pair of real numbers. So a complex number is just an ordered pair. Ordered pair of real numbers is a complex number. And of course, there's more structure than that, which we will discuss right now. Real numbers, okay? And they can be interpreted as points on the complex plane. These are points on the complex plane. And the complex plane is usually denoted as big C, the double strike big C, kind of like R with an extra bar. Okay, so this is points on the complex plane. And the real axis is the x-axis. So this is a real axis. And often we use the notation RE to denote the real axis instead of x. X or RE can be used for the notation for the real axis, and IM is the imaginary axis. Okay. So real numbers are points on the real axis. It's my cat. Real axis is all real numbers. Okay, and then you have the imaginary axis. Imaginary axis, except for 0, okay, are the purely imaginary numbers. Imaginary axis minus 0 are purely imaginary numbers. Just some terminologies. Okay, don't let the terminologies actually fool you, because the term imaginary is historical. Okay, it doesn't make those numbers quote unquote less real. They exist in a very well defined mathematical sense, and I made a video called Demystifying Complex Numbers in 300 years. So go check that out if you want to see an algebraic construction of this object. Okay, let's put a point. This is usually denoted as z. Okay, z equals x and y as an ordered pair. Okay, and when x is a real number, you can write x equals x0. Okay, okay, and this is a special point on the imaginary axis called I. I is the point 0, 1. Okay. Okay, so that's the first picture. The real numbers x and y. X is called the real part, and y is called the imaginary part. And we write if z equals x and y, we say, let me just reorganize this a little bit. We say x equals RE of z. Yeah, x, we write x equals RE of z, and y equals IM of z. Okay, so that's the terminologies. Let me just highlight these. Okay, and we now define equality. You have two real numbers, say two complex numbers, z1 equals z2 if and only if their real part matches and their imaginary part matches. So basically the same point on the complex plane. So this is all perhaps expected. But perhaps, once again, this definition is perhaps not completely redundant, because after all, you can think of fractions as ordered pairs as well, right? You can think of, say, 3 over 4 as an ordered pair, 3, 4. But two fractions don't have to be this. So in order for two fractions to be equal, you don't need to match the numerator and denominator, right? So there's an equivalence relation on the ordered pairs that represent a fraction that don't require strict equality. Right? In complex numbers, we do require that. Okay, they need to be the same point on the complex plane to be equal. Okay, now we have we can define addition and multiplication. So the sum is defined as such. So for let z1 equals x1 y1 as an ordered pair, and z2 as x2 y2 as an ordered pair. Right, the sum is defined as follows: z1 plus z2 equals x1 plus x2 y1 plus y2. That's just a component-wise addition, very straightforward. Okay, and this is defined in the Brown and Churchill labeling. Actually, I need to start to label my equations. This is equation 1, z equals x and y, an ordered pair. Okay, and this is equation 2. Those two are equation 2. Okay, and this is equation 3 in the textbook's labeling. Okay, and now we have the product. Product is a little bit complicated. I'll motivate that very quickly. So the product is as such: x1 y1 times x2 y2 is as follows. It's x1 x2 minus y1 y2 and x1 y2 plus y1 x2. This is equation number 4. Okay, so where does this product definition come from? Right. So this is not in the textbook. I mean, but I think it should be mentioned. Okay, so basically the motivation is as follows. Let me change the color. Which color is better for motivation? Perhaps this blue, huh? Motivation. The motivation is as such because in the study of cubic equation, okay, the details can be found in my video called Demystifying Complex Numbers. Okay, we need to multiply things like x plus y times the square root of minus 1. We need to multiply expressions of the form, okay, x, let's just write, yeah, x plus y times the square root of minus 1, like this. Okay, so basically the cubic formula will give us an expression like this, will involve expression like this. Right. So of course this is rather unsettling in the medieval time. So what people did in Renaissance Italy actually was that we just assume that the square root of minus 1 has a square of minus 1, because that's the most natural definition. Okay, so assume this is okay. Assume you can multiply them and the square root of minus 1 behaves like regular numbers. Okay, then you get x1 x2. Just expand the product, x1 x2 times x plus x1 y2 square root of minus 1, and then plus y1 square root of minus 1 times x2, and then plus y1 y2 times minus 1, because we use the rule square root of 1 square root of minus 1 times square root of minus 1 equals minus 1. So now we can combine the terms, right? So x1 x2, that's a real number, minus y1 y2, that's also a real number, so they can be grouped together. Okay, and the two middle terms has a common factor of square root of minus 1, so it's x1 y2 plus y1 x2. Okay, and this is the motivation for the product. Okay, and now here we're just writing this without the square root of minus 1 symbol. Okay, the square root of minus 1 later will be rigorously defined. because we will define what it means to take a root for the complex number in general, and then discuss the square root of -1. Okay, so right now we're just not using this definition, this definition of the square root, but instead just work with ordered pairs. Okay, so that's it's an operation defined on ordered pair. So nothing is mentioned about numbers whose square is -1 yet. Okay, so now with this definition, what can we say? When the imaginary part is 0, the equations 3 and 4 just becomes the usual operation of addition and multiplication in the set of real numbers. What do we mean? So observation. When y1 equals y2 equals 0, so 3 and 4, 3 becomes z1 plus z2, or let me just say 3 is z1 is x1 0, right? That's your first complex number, and z2 is x2 and 0. You just get x1 plus x2, 0, 0. 0 plus 0, which is 0. Okay, so this is 3. And 4 now becomes x1 0 times x2 0. And the multiplication now becomes x1 x2, okay, minus 0, so nothing needs to be added, and because y are 0, the imaginary part is once again 0. So what is happening here? It feels like these are just regular operations on the set of real numbers, and to be completely formal, we say this is a field isomorphism. Let me write it that way. So the set of complex numbers, the bottom line is, the conclusion is that complex number of the form complex numbers of the form x0, where x is real, can be identified as real numbers. As just x, real number. So the technical language is field isomorphism. Okay, so for more details on field isomorphism, see the video called 300 Years of Demystifying Complex Numbers. Over there, we will give a definition of isomorphism, things like that. Okay, but here you can just treat it as the intuition that even though the actual object, literal object, is x0, discarding the second coordinate, discarding the second component in the ordered pair, loses nothing. And what remains behaves just like real numbers. Okay, that's enough. Okay, so therefore, through this identification, a real number can be seen as a subset of complex numbers. But literally what happens is there is a subfield of complex numbers that is isomorphic to the real numbers. Okay, So there you go. That's the first observation. Next observation. Observation 1. Okay, next observation. So now let's consider writing z. Okay, because now we have the rule of addition, we can write an arbitrary real number, complex number z equals x and y as the sum of x0 plus 0 and y. Okay, this is one observation, and there's another observation. So that is, if we multiply 0, 1 and y0, multiply 0, 1 and y0, let's do the multiplication. Okay, so here's the rule. So you get x1 times x2, that's 0 times y, which is 0, minus y1 times y2, which is minus 0, 1 times 0, so the first coordinate is 0. The second coordinate, x1 times y2 plus y1 times x2, is what? Is 0 times 0 plus 1 times y, so that's 0y. Okay, so together, combine those two, we can write z equals x0 plus 0, 1 times y0, which is going to replace the last term in the first equation, okay, as 0, 1 times y0. So, well, we just argued that complex number of the form x and 0 can be identified as a real number x. So the first one is just x. Identification. Okay, and this y0, for the same reason, can be identified as a real number y. But what is 0, 1? Let's do one more calculation. 0, 1 times 0, 1 itself. Okay, that's 0, 1 squared. Use the multiplication rule again. Okay, let's use the multiplication rule. x1 times x2 minus y1 times y2. So that's 0 times 0 minus 1 times 1 gives you minus 1. And next, you have x1 times y2 plus y1 times x2. So that's 0 times 1 plus 1 times 0. So that's a 0. But minus 1, 0, this is a real number. This can be identified with the actual real number minus 1. And here we've seen a complex number whose square is minus 1. So now we're going to give 0, 1 a special name. Let's define that. This is the definition. Definition: I equals 0, 1 as our special complex number. And theorem: I squared equals minus 1. So here, this 0, 1 can now be denoted as I. And now this is our notation, okay? So now it can be denoted as I, and from now on we're going to write complex number in the famous notation z equals x plus iy. Okay, this is z equals x plus iy, and from now on the ordered pair notation x and y and z equals x plus iy will be used interchangeably. Okay. So this is actually our dominant notation from now on, x plus iy, because with this notation and the rule I squared equals minus 1, you don't need to memorize the product definition anymore. You just expand as usual and pretend not pretend. I keep saying pretend is a bad habit. I is an actual object that actually exists. Okay, it's not fake. It's not a mathematical. It's not a mathematical fiction. I actually exist. exists as a member in a field. Okay, I is a special member in the field. And for more detail, see the demystifying complex numbers video. Demystifying complex numbers. Okay. Okay, so that's the arithmetic defined and the notation x plus iy explained. Okay, so and now you can rewrite 3 and 4 as follows. And by the way, I did not label a few equations. So this equation, here we are at 4 earlier, the definition of multiplication, x plus iy, this is 5. This is equation 5, and I squared equals minus 1, this is equation 6. Okay. So now the addition can be rewritten as sum, okay, x plus iy, x1 plus iy1, okay, plus x2 plus iy2 is just x1 plus x2 quantity plus I times y1 plus y2. Okay, that's the sum. And the product is x1 plus iy1 multiply by x2 plus iy2, and this is x1 x2 minus y1 y2 plus I of y1 x2 x1 y2 plus y2 x1. And these are equations 7 and 8 in the textbook. Okay, there's that. So, no need to memorize the formula, just expand as usual and use the rule I squared equals minus 1. And equation 8 also tells us that any complex number multiplied by 0 is 0. Z times 0 is always 0. Okay, so of course 0 is identified as the real number 0, which is really a ordered pair 0, 0, right? So let's do the multiplication. Z is x plus iy times 0 plus I0. Expand as usual, you get just 0 plus I0, which is 0. Okay. Simple. All right, so that's the definition of sum and product in the field of complex numbers. Okay, and now let's go to the second section called basic algebraic properties. Okay, basic algebraic properties. Chat has been real quiet. Okay, I mean, I'm doing kind of a speed run / marathon, but you can still discuss and ask questions and whatnot. Perhaps this is too basic to ask questions, let's be honest. But once again, we don't assume a prior background in complex variables. Okay, because I mean, on this channel, this is already covered a few times already, but I want to make the live stream or video self-contained. Okay, various properties of addition and multiplication of complex numbers are the same for real numbers. Now, we list here the more basic of these algebraic properties and verify some of them. Most of the others are verified in the exercises. Okay, so now we have the first property in the equation 1 in section 2, is commutative law. So commutative laws are as follows. So you have z1 plus z2 equals z2 plus z1, and z1 times z2 equals z2 times z1. Okay, so these two are labeled as equation 1 in the book. All right, commutative laws. And now also we have associative laws. Associative laws allows us to not specify order in addition and in multiplication. So addition have satisfied the associative law, so that's z1 plus z2 quantity plus z3 equals z1 plus z2 plus z3 quantity. Okay, and also you have z1 times z2 quantity times z3 equals z1 times z2 z3 quantity. It's just a straightforward computation when it comes to the proofs. Okay, so it's not proven in the main text. I do believe we were asked to do so in the exercise, and which we'll also do. Okay, this is I said this is a marathon, but we're not going to actually hand wave stuff. Okay, we'll do it in a pretty comprehensive manner because initially I planned the complex video series to be, this kind of slow and steady series, but now we're getting into, as I said earlier, quote unquote, the deep water of applied mathematics. Complex variables sort of need to catch up, so I figured, you know what, screw it, I'm just gonna do a marathon and cover this stuff as quickly as possible. But still, no shortcut. Okay. Anyway, so that's the two laws, and also you have the distributive laws. Okay, they might look trivial, but it's kind of a miracle that these laws actually survives. These laws from real numbers actually survives. It's not completely obvious why they should be true simply by adding. Oops, what's going on? Okay, something is messed up with the cursor here. Okay, now it's fine. Actually, just distributive law, okay, not plural. Distributive law says, of course, z times z1 plus z2 is z1 plus z2. This is 3. Distributive law. Okay. Okay. So here's an example given in a textbook of how to prove these results. Of course, as I said, it's just a direct verification. It's a computation. So if z1 is x1, y1, z2 is x2, y2, okay, then z1 plus z2 equals x1 plus x2 and y1 plus y2, which is of course the same as x2 plus x1 and y2 plus y1, and this is of course the same as z2 plus z1. So that's the first commutative law verified. Okay. So because of the commutative law, by the commutativity, we can write z equals x plus iy, or z equals x plus y yi as well. These two are equivalent. Okay, and because of associativity, you can get rid of the bracket in an expression that only involves addition, or in an expression that only involves multiplication. But of course, you cannot get rid of the bracket in expression that mixes addition and multiplication. Right? Just common sense from elementary school. Okay, so by associativity, expressions such that z1 plus z2 plus z3 is well defined, and z1 times z2 times z3 are well defined. These expressions are well defined. Of course, you can generalize this to any finite sum or finite product. Okay, nice. And also we have the additive and multiplicative identity. Okay, so there you go. So we have the additive identity called 0. Zero, which is just the ordered pair 0, 0. It satisfies the property that 0 plus z is always z. It changes nothing in the addition. Okay, for addition, if you add in 0, the original number 0 is unchanged. And multiplicative identity, which is 1. Okay, 1 is 1, 0, of course, and 0 times 1 is just z. Now let's verify that. So x plus iy times 1 plus i0 is x1 times x2 minus y1 times y2, so that's just x. The real part is x. Okay, and imaginary part is x1 times y2, that's x times 0, and then plus y2 times x1, that's y times 1. So it's just y. So the result is x times x plus iy. Therefore, z times 1 is z. This is verified. Okay, and those two equations together are labeled as equation 4. Okay, nice. Actually, in fact, 0 and 1 are the only complex numbers that satisfy such properties. Okay, this is an exercise which we will get to shortly. So, furthermore, additive identity and multiplicative identities are unique. This is exercise number 8. We will get to exercises as well. But we won't just read the main text and write a bunch of equations. No, we're actually going to do exercises. Okay, so this is the identities. So with the identities, you can now define subtraction and division. So the additive inverse is defined as follows. So additive inverse is minus z. Minus z is defined as minus x minus y. This way, this is our definition of minus z. This way, z plus minus z is always 0. Okay, and it is a result that the additive inverse is unique for each given day. Additive inverse is unique for each given day. Okay, that's additive inverse. And for multiplicative inverse, which we write as z to the minus 1. So z to the minus 1's expression is slightly more involved. Let's write that down. It's x minus iy over x squared plus y squared if z is non-zero. And this satisfies z times z to the minus 1. Z inverse is 1. Okay, So yeah, this is only defined for z non-zero, just like in this case for real numbers. And multiplicative inverse is also unique. For each z non-zero. And here let's derive the formula for z to the minus 1, derivation. Of z to the minus 1. Okay, so consider a complex number. Let w to be u plus iv such that w times z is 1. Z is non-zero and z equals x plus iy. Okay, so let's try to solve for u and v. As follows. So let's solve for uv. Well, just we have u plus iv times x plus iy is 1. Okay, and therefore by expansion you get ux minus vy plus I times uy plus vx. This is 1. So now we have to compare the real part and imaginary part. Real part equal tells us ux minus vy is 1. Imaginary part equal tells us we have vx plus uy is 0. So this is a system of linear equations for u and v. And you can write that in matrix form. I mean, I like to do that for the system of linear equations. So x and y are treated as fixed numbers. So you can write it as a matrix vector multiplication. The vector is xy, and the matrix on the left, oh actually no, x and y are given, my bad. U and v are the unknowns, x and y are given. So the matrix coefficients are x minus y for the first row, and v, u, what am I talking about? X and y. Yeah, x and y in the second row. Oh, actually, I'm sorry. I should probably change the order, huh? I should probably write it uy plus vx. I don't know why I did that. Here, it should be uy plus vx. X and y are given. Okay, so the coefficient is y and x for the second row. And this is supposed to be equal to 1 and 0. 1 and 0. So there you go. And let's apply the inverse matrix formula to get u and v. Okay, so u and v is the inverse matrix of the 2 by 2 matrix x minus y, y and x times uv. Oh, first of all, actually, let's verify it has a solution. It has a solution because the determinant is non-zero. The system, let's call it star. The system of equations, the system, okay, star of equations in u and v has unique solution. Has unique solution because the determinant of the matrix is non-zero. X squared plus y squared. This is non-zero because we assume z is non-zero. Okay, so now we can write down the solution. This is the unique solution. And the unique solution is 1 over the determinant. That's the 2 by 2 inverse matrix formula, okay? 1 over the determinant, so that's 1 over x squared plus y squared times the, oh, what am I doing? This is 1, 0. Oh my God. This is 1, 0, okay? Not UV. Okay, and now for the matrix element, on the main diagonal, we exchange the order, so it's still x and x. For the off diagonals, we change the sign. So this looks like y here minus y here, times 0, times 1, 0. So this way you get x times 1 plus 0 times y. Okay, that's just x. 1 over determinant is still here, and minus y. So as a result, u and v are now found. So w equals u plus iv is x over x squared plus y squared minus y over x squared plus y squared. Okay, so this is a formula for the multiplicative inverse. Of course, there's no need to memorize this, okay, as we will see later on. Okay, perhaps let me just give it now right away. We'll define that later, talking about the details later. So basically, you can memorize this as follows. This is a shortcut. Shortcut for memorization. Okay, 1 over z can be written as z bar over z times z bar. I know we haven't introduced z bar yet, but z bar is called the complex conjugate. Okay, x plus iy bar is x minus iy. Okay, so that's x minus iy. Okay, here on the bottom, z times z bar is always a real number, a non-negative real number, x squared plus y squared. And on top is just x minus iy. Okay, we'll be using this multiplication by a conjugate trick a lot. Okay. All right, so now you have the multiplicative inverse now defined. Let's do the exercises. Exercises. So 1, we want to verify some identities. So, I mean, we can, for the sake of the video, we'll just treat them as calculation problems. Okay, so 1 is calculating square root of 2 minus I times 1 minus square root of 2I, like that. Okay, so square root of 2 minus I minus I, okay, plus minus you get a plus sign, plus square root of 2I squared. But I squared is just minus 1. So it cancels out with the minus 1 up there in the beginning, so you get minus 2i. Okay, simple. Next up, 2 minus 3 and minus 2, 1. Okay, so let's write it as the I notation. So you have 2 minus I3. Okay, 2 minus I3 or 3i. Let's write 3i, perhaps it's more natural. And then you have minus 2 plus I. Expand that, you get the real part, which is 2 times minus 2. That's a 4. And then you have minus 3i times I. That's a real number too, so that's minus 3i squared, so that's a plus 3. Okay, imaginary part, that I times 2 plus minus 3 times minus 2, that's a 6. So together you get minus 1 plus 8i. The original equation is in ordered pair notation, so let's just write that as ordered pair notation as well. So that's minus 1 and 8. That's it. Okay, simple. Simple calculation to for complex multiplication. C, we have 3, 1 ordered pair times 3 minus 1 times 1/5 and 1/10. Okay. You can do these whichever way you want, obviously, because earlier we said associativity allows us to do so. Okay. And let's see. So let's shall we convert this to I notation, or shall we just keep it in ordered pair notation? You know what? I'm just more used to the I notation. Okay, so let's rewrite. Okay, so multiply the first two, you get 3 times 3 is 9. And you got a minus I squared, so that's a plus 1. Okay, and then times quantity minus 3i. Okay, this is minus 3i plus 3i. Okay, so yeah, well, I should have recognized this because this is just 3 plus I times the conjugate, or 3 plus I. So that's just 3 squared plus 1 squared. That's 10. So that's 10 times 1/5 plus 1/10 I. And as a result, you get 2 plus I. Okay. And rewrite this as ordered pair notation, you get 2, 1. That's it. Okay, so that's the first question. Very, very simple. Second, you want to show that A, the real part of IZ equals minus imaginary part of Z. And B, imaginary part of IZ equals real part of Z. Okay. Should be an easy proof. Let Z to be X plus IY. So A, what is IZ? IZ, this is I times X plus IY. This gives you minus Y plus IX. Therefore, the real part of IZ is minus Y, which is minus the imaginary part of Z. Okay, this proves A. B, you have imaginary part of the IZ. Actually, just write it this way. Okay, therefore, imaginary part of IZ can be followed after. Imaginary part of IZ is X, which is the real part of Z. Okay, done. Okay, so next question, number 3. Next question, show that. You see, the exercises of this book is very approachable. Of course, this is just the first 2 questions. There are more difficult questions in the later chapters, of course. So we're just going to just speed run through this. These simple exercises. X plus 1 plus z squared is 1 plus 2z plus z squared. Okay, here's the proof. We're going to write it in a more careful way. Let's try to justify each step. Okay, so 1 plus z squared, by definition, is 1 plus z times 1 plus z. Okay, let's just specify that it's just a definition of power or square or squaring. Definition of squaring. Okay, and now let's use the distributive law. By the distributive law, you get 1 plus z times 1 plus 1 plus z times z. This is the distributive law. Okay. So in the distributive law, the original distributive law, here, the sum is on the right, but of course we know if the sum together is on the left, it wouldn't matter because of the commutative law. Okay, but we're just going to follow strictly these laws. Okay, by a distributive law, we mean this literally. Okay, so let's do a commutative law to exchange order in our derivation. So this is the same as 1 times 1 plus z times 1 plus z. Commutative law. And then you use a distributive law to expand once again. So that's 1 plus z. Okay, and then plus z squared. This is distributive law again. This is commutative law for multiplication. Earlier, that step. Okay, and now you can use associativity and write 1 plus z this way. This is associativity or associative law for addition. Okay, and then combine the 2z, you get 1 plus 2z plus z squared, exactly as we needed. So we're done. Okay, so that's the third question. 4. It asks us to verify z equals 1 plus or minus I satisfy, okay, both of them satisfy z squared minus 2z plus 2 equals 0. Okay, once again, this is just a computation. Left hand side, z squared minus 2z plus 2. Okay, you can do the two operations together. You can do that, but it gets complicated. Sorry, it gets confusing. Okay, so you get a plus or minus sign, and then you square it. You know, it's just a math. So we're gonna do things separately. Okay. Hang on, let me just drink some water. Okay. So yeah, z equals 1 plus I. Then z squared minus 2z plus 2 is 1 plus I squared minus 2, 1 plus I plus 2. And this is 1. Okay, we use the previous identity, 1 plus z squared. I use that. So 1 plus 2i plus I squared. Okay, and then minus 2 here, what's going on? Minus 2i, and then plus 2. So everything cancels. So 1 and I squared cancel, 2i and minus 2i cancel, minus 2 and 2 cancel. You get 0. Okay, and z equals 1 minus I. Do the calculation again. Z squared minus 2z plus 2 here is 1 minus I quantity squared minus 2 times 1 minus I plus 2, and this is just 1 minus 2I plus I squared minus 2 plus 2I and then plus 2. Same business. Everything cancels. Get 0. Okay, done. Okay, 5. We want to prove multiplication of complex numbers is commutative. Prove commutative law. For multiplication. Okay, simple. So let z1 equals x plus iy, x1 plus iy1, z2 equals x2 plus iy2. Okay, then z1 times z2 is x1 plus iy1, x2 plus iy2. This is x1, x2 minus y1, y2 plus I, x1, y2 plus y1, x2, y1. Okay. And now let's calculate z2, z1, and then compare x2 plus iy2, x1 plus iy1, and you have x2, x1 minus y2, y1, and then plus I times x2, y1 plus y2, x1. Obviously, these two are the same. And this is because real number multiplication is commutative. Since real number multiplication is commutative, z1, z2 equals z2, z1. And we're done. Okay, next up, number 6. Verify the associative law for addition for complex numbers as stated in the beginning, as well as distributive law. Okay, so prove associative law for addition. And distributive law. Okay, here's the proof. So let zi, okay, x equals xi plus, let's not use I to avoid confusion. Let's use n. We have three complex numbers, zn equals xm plus I yn. N equals 1, 2, and 3. Okay, and now we have the following. So let's first calculate, okay, z1 plus z2 quantity and then plus z3. And this is just x1 plus y1i plus x2 plus y2i quantity, and then plus x3, which is x3 plus iy3. Okay, and this way, this is just x1 plus x2 quantity plus I times y1 plus y2 quantity, and then plus x3 plus iy3. Okay, and together you get x1 plus x2 plus x3 plus I times quantity of y1 plus y2 plus y3. There you go. And repeat z1 plus z2 plus z3 quantity is x1 plus y1i okay, and then plus the quantities x2 plus y2i plus the x3 plus y3i. Okay, this is x1 plus y1i plus x1, okay, x2 plus x3 plus I y2 plus y3. Okay, and now you get x1 plus x2 plus x3 bracket plus I y1 plus y2 plus y3. Therefore, z1 plus z2 plus z3 equals z1 plus z2 plus z3. Okay, so that's the associative law verified. Distributive law. Okay, say let's calculate z1. Therefore, this verifies the associative law. Okay, for addition, z1 times z2 plus z3. Let's calculate that. Okay, so this is just we calculate z2 plus z3, so we can use that. So x1 plus here we go, x1 plus iy1, and then plus, and then times the quantity x2 plus x3 plus I y2 and y3. Okay, multiplication, you get x1 times x2 plus x3 minus y1 times y2 plus y3. Okay, and then plus I times y1 x2 x3 plus x1 y2 plus y3. Okay, expand x1 x2 plus x1 x3 minus y1 y2 minus y1 y3. Okay, and now you have the imaginary part, which is y1 x2 plus y1 x3 plus x1 y2 plus x1 y3. That's it. Okay, and the other side, the right hand side of the distributive law, is z1 z2 plus z1 z3. Let's go. z1 z2 is x1 plus iy1 times x2 plus iy2 plus z1 is x1 plus iy1, z3 is x3 plus iy3. Expand the product, you get x1 x2 minus y1 y2 quantity plus, okay, I of x1 y2 plus, okay, y1 x2 Okay, next product is x1, x3 minus y1, y3. Okay, and then you have a plus I x1, y3 minus y1, x3. Okay, got it. Now you have the two summation. Let's expand. You get x1, x2 plus x1, x3 minus y1, y2 minus y1, y3, and then plus I x1, y2 plus y1, x2 plus x1, y3 minus y1, x3. Oh, actually this should be plus. Sorry. Let's compare. They should be the same. Yeah, x1, x2 here, x1, x2 plus x1, x3. Yeah, plus x1, x3 minus y1, y2 minus y1, y2 minus y1, y3 minus y1, y3. Okay, in the imaginary part, y1, x2. Yeah, we have that. y1, x3. Yes, we have that. x1, y2. Yes, we have that. x1, y3. Yes, we have that. Okay, so all checks out. Therefore, z1 times z2 plus z3 equals z1, z2 plus z1, z3. This verifies the distributive law. Okay, great. Okay. So these aren't particularly glamorous tasks, okay? They don't require ingenuity or anything. They can be quite boring, you might want to call it that way. But, you know, sometimes we prove these things to secure the foundation, okay? So keep going. Let's pat ourselves in the back for being thorough, okay? And now let's do the following. So it says, 7, the next question, 7, it says, use the associative law for addition and the distributive law to show that, okay, to show z times z1 plus z2 plus z3 is expandable equals z times z1 plus z times z2 plus z times z3. Okay, so doing so, we first interpret. Okay, to interpret the addition as such. Okay, z times z1, z times z1 plus z2 plus z3 is z times you can interpret this addition in either way. You can add z1 and z2 together, or you can add z2 and z3 together, so it does not matter. Okay. Because of associative law, you can make this interpretation here. So the use of associativity is implicit here. Implicitly. Because without associative law, this expression would not make sense. It's like in vector algebra, the cross product. If, say, you have three vectors, A, B, and C, A cross B cross C, this is undefined. This is a bad expression because it's ambiguous. In vector algebra, if you calculate the cross product of the first two vectors and then cross with the third, the result is not the same as A cross the cross product of B and C. They aren't the same, so therefore you do not have associativity there. You don't have associativity, and therefore you don't get to write expression like this. This is meaningless. Here, we're using the associative law implicitly. Because of associative law, this expression is meaningful. Okay, because the order of the precedence. Okay, I should put this. The precedence don't matter. Okay, so now we have just two terms adding together. You can use a distributive law, say z times z1 plus z2, and then plus z times z3. That's distributive law. Okay. Okay, that's nice. And then let's keep distributing. Right, the first term can now once again be written as z times z1 plus z times z2 quantity plus z times z3, thanks to distributive law. Okay. And now, once again, let's use associative law implicitly to get rid of the bracket. So, and that's exactly what we wanted. So z times z1 plus z times z2 plus z times z3, and we're done. Okay, that's the seventh question. 8. It says, okay, by the way, 8 was something that we promised earlier, proving that additive identity and multiplicative identities are unique, exercise 8. And this is how it's done. 8. So, here. Okay. Eight, we want to prove that additive identity is unique. For a given complex number. Okay, so that's part A, proof. Let z equals x plus iy. Okay, suppose w satisfies. Actually, let's give w coordinates. W equals u plus iv. Okay. Yeah, suppose w satisfies z plus w equals 0. And therefore, we have x plus iy plus u plus iv equals 0. And this is the same as x plus u quantity plus I times y plus v equals 0. So the real part is 0, x plus u is 0, and y plus v is 0. So therefore, u must be minus x and v must be minus y. So w is unique. Okay, so that's the additive identity, uniqueness, now proved. Part B. So here, actually, part B is to prove that the multiplicative identity is unique. However, we already did that. Right? So in the textbook, the formula for the multiplicative inverse was given. But this derivation here proved uniqueness. Here we showed because this is a linear system of equation and the determinant is non-zero, so it has a unique solution. So this is actually just exercise part B. So let me just actually call that exercise part B. Or perhaps add a remark at the end. Remark. This is also exercise 8, part B, uniqueness of multiplicative identity. Okay, so sorry, I'm speaking Chinese. Part B is done earlier. Uniqueness is now proved for multiplicative identity. Okay, great. 9, also pretty trivial exercise. We want to show minus 1z is minus z. Okay, so here we're actually going to use the relevant definition. So for example, what is minus 1? Well, minus 1 is the complex number, the ordered pair, minus 1, 0. Okay, and what is minus z? Minus z is the additive inverse of z. So let's use those definitions. Proof by definitions. Okay, so actually let z equals x plus y, x plus iy. Let z equals x plus iy. Okay, I'm going to put it here. Z equals x plus iy, and by definition, minus z is minus x minus iy. Okay, and also minus 1 is minus 1 plus I0. Okay, so the left-hand side, which is minus 1 times z, can be written as minus 1 plus I0 times minus x minus iy. Multiplication gives us, this is x. Oh, hang on a second. What am I doing? This is minus z, not z. Okay. Sorry, that was me yarning. Okay, I might need a coffee or something, but it's okay. Let's keep going. You get minus x minus, minus x minus y plus I. Oh, sorry, no, that's not right. That's not right. Minus x, okay, minus 0. That's the real part. And then plus I times 0 times x and then minus y, which is exactly minus x minus iy, which is minus z. Okay, so we're done. That's 9. Number 10. Once again, just wanted to verify an identity, which says show minus iy equals minus I times y. Okay, so once again, we need to in the exercise it shows that it says in the exercise, in the wording of the textbook, it says the additive inverse of a complex number the additive inverse of z equals x plus iy can be written as minus z equals minus x minus iy without ambiguity. Yeah, so yeah, basically minus I can be grouped with the minus sign. Yeah, the I can be grouped with the minus sign. That's what it means. Ambiguity. Okay, so all right, is that a? Oh yeah, y is a real number. Well, y is a real number. Okay. Okay, so um, solution is as follows. So what is IY? Let's first calculate IY. Y is a real number. So here, the two, when interpreted as complex numbers, is as such. So that's a 0, 1 ordered pair times y0 ordered pair. Okay, and then you have the multiplication, right? So that's 0 times y, that's a 0, minus 1 times 0, that's also a 0. Okay, the real part. Imaginary part is 0 times 0, that's a 0, and plus 1 times y, which is a y. So this gives you 0 and y, as expected. So therefore, minus iy is minus 0, which is 0, and minus y. So this is the left-hand side. The right-hand side, let's calculate minus I times y. Minus I is to be interpreted as 0 minus 1. And y is y0. Do the multiplication again. Let's just calculate 0 times y, which is 0. Okay, plus minus 1 times 0, which is plus another 0. Imaginary part is 0 times 0, that's a 0, and then minus y. So that's a 0 and minus y. Okay. You see, I might have shot myself in the foot. You know why, guys? Because I was planning to do this marathon, so I had a big meal before, and now I'm sleepy. You see, this is I kind of screwed myself over. Which remind me, well, too late, that there was a mathematician called Littlewood. Guys, you might know him. You might heard of this person. He was a frequent collaborator with G.H. Hardy, Littlewood, mathematician, British mathematician. Okay, he collaborated a lot with Hardy. He worked in analysis, number theory, and differential equations, and has lengthy collaboration with Hardy, Ramanujan, and Mary Cartwright. Okay, and he had a little fantastic book called Littlewood's Miscellany, I believe, which is a combination of his memoir and actual mathematics, which is pretty cool. So he worked during the World War I. He served in artillery corps. He made highly significant contribution to the field of ballistics. Littlewood is also remembered for his reminiscence, a mathematician's miscellany, in which he said, okay, he don't eat a lot before a work. Okay, he has like a some sort of meal requirement before working, and he said, and he don't eat a lot because this way he gets to like concentrate his brain power. Okay, the blood flow is now concentrated in the brain instead of in the stomach. But unfortunately, I forgot that advice, and I had a big meal because I was planning, oh, I'm gonna do this in like a 10-hour marathon. But then I ate a lot. Now I'm sleepy. I kind of screwed myself over. This is a fantastic book. It's got interesting problems. in there. It's a very unique book. I hope I get to cover it someday. I think, in my opinion, this is a much better book compared to Hardy's A Mathematician's Apology. I think most people in the math community know Hardy's A Mathematician's Apology. I don't think this was a very good book at all. It's actually pretty sad, and it's very judgmental, considering Hardy's mental state at the time, because he was in a very depressive state. Okay, so it's better read as a cautionary tale. The reason is simple, because Hardy did not enter mathematics with the right motivation. Okay, so who am I to take shot at a giant like Hardy? Because he said it in the apology himself. He admitted himself that he initially had little natural interest towards mathematics. So the interest was not intrinsic. Instead, Hardy was a very insecure person. Personality-wise, Hardy was a very insecure person, and he wanted to use mathematics to kind of, and just good grades in general, academic achievement in general, to gain self-image, to gain self-worth. That was his original motivation. And also, Hardy was fiercely atheistic, and he wanted to prove his superior intellect. But later on, his productivity fell, and as a result, his self-image collapsed. It's a very tragic person. And he wrote this book as a lament. And so this one is, mathematically speaking, a lot less interesting compared to Littlewood's Mathematician's Miscellany. There's lots of interesting problems in this book and the thought process of a working mathematician. Okay, so yeah, definitely go check out A Mathematician's Miscellany, and I think I will give a more casual stream for these two books, comparing these two books. Okay, just, you see, a healthy mind versus an ailed mind. Okay, I mean, Hardy himself, of course, he made great contribution to British mathematics. He put British pure math on the map before so prior to the early 20th century. Analysis was mainly the field of French and German, and to some extent also Italian mathematics. British mathematics was severely lacking behind when it comes to pure analysis, right? So, for example, in the complex analysis work, like Brown Churchill, I don't think there is a single result named after a British mathematician, because the fundamentals were established by French and German mathematicians, Cauchy, Riemann, Weierstrass, those people. British mathematics at the time was still mostly focused on mathematical physics, although they did very well in there. People like Stokes, Maxwell, Kelvin made fundamental contributions to electrodynamics, fluid mechanics. So it's very physics-oriented mathematics, and it's lacking behind in pure analysis. Hardy, on the other hand, championed pure mathematics, and he put British pure math on the map. So there's no denying of that whatsoever. And he also helped Ramanujan a lot. Ramanujan was discovered by him. His talent was discovered by him. And Ramanujan, being an Indian, invited to Cambridge, faced a lot of institutional prejudice because he worked rather unconventionally, and he was also not white. Let's be frank. So a lot of people thought he was a crank. But Hardy recognized his true genius. And the friendship between them were very moving. Right? But at the same time, Hardy was also a flawed person, a deeply flawed and so he was a vulnerable person. He was extremely shy, as a child and socially awkward, cold and eccentric throughout his life. During his school years, he was top of his class in most subjects and won many prizes and awards, but hated having to receive them in front of the entire school. He was uncomfortable being introduced to new people and could not bear to look at his own reflection in the mirror. It is said that when staying in hotels, he would cover all the mirrors with towels. You see? But the thing is, Hardy, in my opinion, is a pretty handsome young man. Let's take a look at his picture. Hardy. GH. You see? He looked like a movie star. I don't know why he hated his appearance so much. You know? It's really sad. And he became friends with Moore, Russell, and Keynes. Russell, of course, everybody knows about Russell's paradox. Keynes is a famous economist. Keynesianism dominated the economic policies during the Great Depression, Second World War, and to some extent after the Second World War. And now it's also one of the main schools of macroeconomics. So he was in this elite club of intellectuals in Britain. Okay, and what was his later life? Yeah, he deliberately pointed out in his apology that mathematics do not glory in the uselessness of their work, but rather because science can be used for evil ends as well as good, mathematicians may be justified in rejoicing that there is one science at any rate, and that their own, whose very remoteness from ordinary human activities should keep it gentle and clean. To me, this is pure fantasy. Hardy get to do what he did because of state sponsorship. Because of he lived in this, he was shielded from the British state. He get to work at Cambridge because of mathematics have been in the past, especially British mathematics, has been so useful that government pumped money to it. And so that even though certain branches of pure mathematics at the time have no direct application, it is the hope that they will become useful at some point. Because history has shown mathematics, even though sometimes you don't directly develop it out of motivation for usefulness, eventually this will become useful. This has been the record of history. So that's why people like Hardy get to be shielded, right, from the quote-unquote the ugliness, the evil of the real world. So this is kind of a what we call a surplus in economics, right? So in early human history, everybody pretty much need to work to get food. Pretty much the entire population was devoted to agriculture. But then productivity grew, so certain people can live off other people's agricultural product and not participating in agriculture themselves, instead do other productive activity. This is the same with mathematics. In early period, mathematician doesn't matter your field application, have to perform some kind of practical duty, for example, astronomy and ballistics, and creating mathematical tables for the government, for businesses. Like even people like Euler had to work for shipbuilding, for Frederick the Great, and help the Russian empress to design their garden. That's the government won't just say, okay, prove this beautiful theorem and we'll pay you. Even for Euler, they had to do it that way because mathematics has been so successful that you can afford to have certain group of people to just do pure mathematics. So pure mathematicians are funded by applied mathematicians. And I really don't agree with his contempt towards applied mathematics. It's like biting the hand that feeds him. You know. So anyway, this is a really sad book. If you treat this as how working mathematicians actually think, you will be very misguided. It's more of a midlife crisis confession than a philosophy of mathematics. Okay. Anyway, that's a nice break, in my opinion. Okay, let's come back to do some more problems. Coming back to 11. Okay, so now we wish to solve for an equation. Solve for z. Solve for z in the quadratic equation. Z squared plus z plus 1 equals 0. By writing z equals x plus iy. Okay, let's do that. Solution. Let's do the substitution. Z squared plus z plus 1 equals 0. Therefore, we have x plus iy quantity squared plus z, that's x plus iy plus 1 equals 0. Okay, let's do the expansion. You get x squared minus 2ixy minus y squared plus x plus iy plus 1 equals 0. So the real part is now x squared minus y squared plus x plus 1. That's the real part. The imaginary part is y minus 2xy equals 0. Okay, so therefore we have two equations. Is a system x squared minus y squared plus x plus 1 equals 0 and y minus 2xy equals 0. So here we have two equations. Let's just call this 1 and 2. This is a nonlinear system. In general, it will be difficult to solve. However, we notice 2 is factorizable. So from 2, we have y times 1 minus 2x equals 0. So we have two cases. Case 1. Okay, case 1, y equals 0. Case 2, y not equal 0. Okay. So if y equals 0, 2 is automatically satisfied, and now 1 becomes x squared plus x plus 1 equals 0. Remember, here x and y are real numbers. Okay, here x and y are real numbers, but this has no real solution, which has no zero solution, has no real solution. Delta is b squared minus 4ac, so that's 1 minus 4, which is minus 3, which is negative. So that's case 1. Okay, so there's this case and there's no solution. And if y is non-zero, then x must be 1/2. X is now solved. So, and as a result, 1 becomes, here you have 1 squared, half squared, half of x squared. So that's 1/4 minus y squared plus 1/2 plus 1. Something is wrong here. Hang on, something is not right. Something isn't right. Did I make a mistake in the expansion? Yes, I did. Here should be plus sign. Yeah, this should be a plus sign. Okay, so that changes things. I made a mistake. Here, this should be a plus sign. Okay, so x should be minus 1/2. Yeah. Okay, x should be minus 1/2. Everything else should be fine. And you get 1/4. 1/4, that's x squared minus y squared minus 1/2 plus 1 equals 0. So therefore, y squared is 3/4, and y is plus or minus square root of 3/2. So that's case 2. So finally, as a result, you have two solutions. X is just minus 1/2, and y is plus or minus I square root of 3/2. And as a remark, this is the same result you would get from using the quadratic equation. You can apply the quadratic equation and get the same result. So z is minus b plus or minus square root of b squared minus 4ac over 2a. So this is just minus b minus 1 plus or minus square root of b squared minus 4ac. That's minus 3 over 2. Same thing. Okay, so yeah, this is consistent with our answer. Okay, so that's all the exercises for section 1 and 2. Okay, I think I would start with a new note, because this is getting a little bit long, and the longer it gets, the laggier the note becomes. So I'm going to start a new note, and this will be August the 14th. Complex variables. Brown and Churchill. How did I name this? Okay, BNC. Okay, BNC complex variables. So that's my 1. Okay. Second note. 2. So how we're doing in terms of time? I started at 9, right? I started at 9, so 2 hours. It's about 2 hours. So I did 2 sections plus exercise. That's okay. So I should be able to finish chapter 1. So chapter 1, guys, chapter 1 has 12 sections. 12 sections. Let's just assume uniform distribution, okay? So I did 2 hours for the first 2 sections. The next 6 hours, no, not 6 hours, multiply that by 6 is 12 hours, half a day. So half a day, finish 1 chapter. That's pretty good progress. Okay, much faster than the measure theory stream. Well, measure theory is a lot harder, so I guess that's fair. Okay, actually, guys, I'm going to use the bathroom real quick, and I'll be back. We'll be back doing some more complex algebra. Okay. Anyway, I'll be back. Hi, I'm back. So now let's do some more complex algebra. This is section 3 called Further Algebraic Properties. Okay, let's go. In this section, we mention a number of other algebraic properties of addition and multiplication of complex numbers that follow from the ones already described in section 2. Inasmuch as such properties continue to be anticipated because they also apply to real numbers, the reader can easily pass to section 4 without serious disruption. Okay, anyway, well, we're not going to skip that. We're going to see what is discussed here. So we begin with the observation that the existence of multiplicative inverse enable us to show that, okay, first property, okay, the existence of multiplicative inverse enabled us to show that if a product, if z1 times z2 is 0, so at least one of the factors z1 and z2 is 0. So this says if z1 times z2 is 0, then z1 equals 0 or z2 equals 0. Okay? Okay, so this is actually a good exercise for proving OR statement. And so here comes some proof technique, okay? Some proof technique. Is a general proof technique for proving OR statement. Okay, it works like this. Let P and Q be propositions. P, not and Q. P, Q be proposition. That is, statement with true and false values, or truth values, either true or false. Let P and Q be propositions. Okay, to prove something like this, to prove P or Q, we can negate P, that is, we assume negative P and then prove Q. We can do one of the following. Okay, one, assume negative P, assume not P and prove Q, or you can assume not Q and then prove P. Let's see why. Although this is intuitive, but it requires a mathematical justification. And the mathematical justification is as follows. Okay, P or Q is logically equivalent to not P implies Q. If not P, then Q. And it is also logically equivalent to not Q and implies P. Okay, let's just quickly check this is actually true. Okay, you can use the truth table to do this. Verify 1. 2 can be verified similarly. So let's verify 1. So here you have 2 columns for P and Q. Now, this is a side note on proof writing and logic. True, 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 false. False, true. False, false. Okay, and then you take P or Q. This is one of the sub-formulas here. And you have negative P, or negative P, yes, and negative P implies Q. Okay. P or Q is true whenever at least one of P and Q is true. So you get true, 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 false, like this. Negation of P is false, false, true, true. Negation of P implies Q, right? Implies, how does imply work? Well, if the premise is false, the whole implication is automatically true. This is known as vacuous truth. And we explain why vacuous truths must exist, why we must have vacuous truths in our introduction to proof video or live stream. Okay, vacuous truth is not just an arbitrary choice. It must exist for logic to work. So yeah, for classical logic to work. So here, for more explanation, you can go check out that proof video. Okay, I'll put it in chat. So hang on, let me try to find it. It's an old video of mine on explaining why imply must be defined in a way that has vacuous truth. Okay, I don't think this is usually very well explained in courses and textbook. So yeah, it was an old video, like about a year ago. Okay, I'll share it in chat. Oh no. Damn it, I missed all the chat. What is going on? I thought there was nothing going on in chat. Everyone just listened to my rambling all the time, like without saying much. Okay, sorry guys. I missed the entire chat. God dang it. Okay. Shit. I need to respond to chat. Okay. Okay, this video explains vacuous truths. Okay, guys, sorry. I'll finish the truth table and I'll come back to answering chat. I wasn't ignoring it. I just saw there's nothing going on in chat. Truth is needed for classic logic to work. Okay, sorry guys, my profuse apology. Okay, going back to the chat, all the way here. Yeah, this is chat. You know what? I was like here. I didn't know it was their message coming. Yeah, engineer definitely need this. You have read Grothendieck book on? No, I have read. I never read anything Grothendieck written. I'm sorry. Okay, so I'll put this down, okay? Is this in French or is it translated? Is this translated? This is in French. Okay, my French is very weak, so maybe I can use the Google Translate it to English. What is it to say? Reflection and testimony on a passage of mathematician. Oh, okay, interesting. So this is probably responding to my comment on Hardy and Littlewood, huh? Is there English version? The French edition, is it translated? Harvest and sowing. Oh, this is so interesting. I'll definitely read this if there exists a translated version. Well, nowadays you can just AI translate, I suppose. But I mean, it's not ideal, but that's better than nothing. I'll be very interested in Grothendieck's perspective. Thank you. Okay. Whole trigonometry gets easy. Exactly. Good evening from Indonesia. Yeah, actually, thank you, Far, for joining the stream. I recognize you. Linear algebra also can be interpreted as a sort using complex numbers, scaling, and rotation. Well, I guess you can say complex numbers is a vector space, right? It's both a real and complex vector space. And complex numbers can serve as the scalar in a vector space as a scalar for scalar multiplication, and complex inner product spaces, just complex vector spaces in general, has its own unique results that are not available in real, just purely real vector spaces. For example, if the thing is, if you only consider real vector spaces, right, then you can have, because if you only consider real vector spaces, then complex numbers can no longer be considered as valid eigenvalues, which is a big drawback, right? For example, a rotation matrix in 2D has no real eigenvalues. And if you only consider real vector spaces, then such matrices will not have eigenvalue, which is a great disappointment. Yes, 0 means ignore or remove the imaginary part. Yes, you can ignore that. Right? So that's the kind of informal justification, informal description for field isomorphism between complex number x0 to x. Well, these cover quaternions or something like how to do complex numbers actually now get defined like as vectors. Assis, sorry, perhaps you asked this question like an hour ago, but we already covered quaternion in the earlier stream on 3D rotations. And I think I'll do a more condensed video on quaternion, like how to do 3D rotation. But this book in particular do not cover quaternions. Okay, this is purely about complex numbers. So yeah, I'll put the link where I covered quaternions here. So live. Oh, here there is a stream for quaternion for 3D rotations. What's going on? Yeah, 3D rotation. Yeah, this one, part 2. So part 1 is a review of vector algebra. Part 2 has Rodriguez formula, namely, given an axis and an angle, how do you do rotation in 3D? And this can be compactly represented using quaternions. So it's here. Okay, this is an applied introduction to quaternion. So yeah, pretty much only about explaining how quaternion encodes 3D rotation. Okay, so I'll put that in chat. Quaternions and 3D rotation. So there we first derived 3D rotations using matrix and vectors and rewrote it in 3D in quaternions. Okay. Oh, thank you, Steve, for your generosity. Riggle, thank you very much for responding to that person, to assist. Yeah, this text does not cover quaternion. Thank you. I mean, yes, it's a touch. It's a touch. It's not a comprehensive introduction because it was a very single-minded mission of describing 3D rotation in quaternion. There's no things, for example, the general study of a non-commutative algebra, where quaternion is a great example of. Okay, this is going to be 2 to 3 hours, probably even longer. As I said, probably 12 hours. This stream helped me focus. Oh, that's great, awesome. I'm glad it helps. Seriously stoked for this marathon in series. Been working through the measure theory one slowly. Oh, that's awesome. That's great. That's great. Awesome. Can't stay long, but love running Churchill. Oh, wow. Math can be a hobby. JC, thanks for joining the stream. Okay. I'm sorry I ignored you. My goodness. Once again, I profusely apologize.
Hi Ming, good morning. What part of the diffusion model book we will be covering next week on the stream? I'm skimming through the first few chapters right now. Good question. Very good question. Here, Sha, if you're still here, I haven't thought through this yet, okay? I haven't thought through it because I haven't got the time. I've been so busy with, the earlier streams and also real life stuff. So Sha was talking about this book. So I think it's called the Diffusion Model by Lai. Yeah, called The Principle of Diffusion Model. So this is a draft version of an upcoming book on diffusion models. Okay, so let's check it out. I think Sha is talking about this book, and well, this is the one I shared it in the Discord, in my Discord. So this upcoming Saturday, well, that's tomorrow, we will be doing stochastic differential equations, and in particular, we're working towards numerical solutions of stochastic differential equations because, after all, that's how SDEs are usually solved in practice, right? And in particular, including diffusion model. SDE diffusion model, if SDE for diffusion model are solved numerically, okay? So I'm going to start the SDE series from an applied perspective, okay? That is to say, I'm only going to assume basic knowledge of ordinary differential equation and probability theory at the level of calculus, okay? No need for measure theory, and ideally speaking, you would also perhaps be better equipped if you know some numerical method for ordinary differential equation, but that's not essential. We will introduce and review numerical ODBs along the way. Okay, so this is going to be very different compared to your standard course on stochastic differential equation, because usually it is very theoretical and calls for very high mathematical preliminaries. Right? SDE is at least a master's level topic, if not PhD. So the usual courses are prohibitively high, right? The barrier of entry for usual SDE courses are prohibitively high. And that's a shame, because right now a lot of people are trying to get into applications of SDEs, including diffusion model, which is kind of very hot topic nowadays. Which chapters I'm planning to do, actually I have no idea. To be honest, I have no idea. So I guess because since I have no idea and I wanted to figure things out myself, I'll just start from the beginning. Okay, I'll just start from the beginning. If I don't understand something, I'll say it out loud. I don't understand this. So please send help, or please don't take my word on it as some sort of definitive word. Because this is my current self-assessment, okay? Current self-assessment. So I don't have background in deep generative modeling, okay? Just traditional. For example, VAE, I mean, I only heard of them, but from a mathematical perspective, I knew nothing about them. But for diffusion-related stuff, I do know a thing or two. Okay, I do know a thing or two thanks to my own background in my graduate study background. I do know a thing or two about the fundamentals of diffusion, stochastic calculus, that sort of stuff. So I do recognize a few familiar names here. Stochastic differential equation, Fokker-Planck equation, that sort of stuff. The unifying lens is a Fokker-Planck equation. By the way, we will derive Fokker-Planck's equation next week. So this week we did two stochastic processor physicist videos or live streams. Einstein's description, Langevin's description. And next week we'll cover Markov process, Master's equation, and Fokker-Planck. It's going to be Fokker-Planck will definitely be derived next week by the time we start the diffusion model. So that's a good thing. We won't have time for numerical methods yet. So my self-assessment is that I have I likely have, say, the necessary ingredient for diffusion model, but I have zero idea currently I have no idea how they stitch together to build the diffusion model. And as I said earlier, because it's not like I already have deep generated modeling experience, so I'll probably start from the beginning and hopefully working things out together and have discussion with you guys. It's very much going to be a community learning experience. Okay, so that's my answer to Sha. So sorry if you left the stream because I ignored your question earlier. It wasn't intentional. Okay, so this is the book. I'll put it in chat. Perhaps this is the first book-length treatment on diffusion model. Perhaps. Okay, I'll put it in chat right now. Book-length treatment on diffusion model. Very hot topic nowadays. So the exercise covers all the property. Yes. Can you link the previous stream? Which one? So might it only be chapter 1 for today? Yes, we're going to do chapter 1 today. Yeah. No, I was talking about the upcoming stream. But Ming, you're partially right about that. Yeah. It includes, yeah, so this is eating. Now I'm actually doing a lot better. So I'm okay. I'm okay now. Is this for first course? Yes. Complex analysis by Brown and Churchill is definitely a first course in complex variables. Very much a first course. Excellent for self-study. Okay. Anyway, I'm all caught up with chat. Hopefully, hopefully I did not disappoint too many people for ignoring the chat. Okay. Anyway, so now I think I'm all well caught up, and let's just put it perhaps here. Maybe do I need the space? Yeah, I think I do need the space, right? Let's just put it on my other screen. Okay, so coming back, this simple property we wanted to prove. If z1 times z2, okay, more question. Okay, anyway, so this is, okay, sorry, I'm not going to explain what a convex cone today. Yes, we will, okay, I can't cover residual theorem today. I will make good progress if I can. I would be making good progress if I can finish chapter 1, which is regions on the complex plane. And residual theorem is like chapter 6. Okay. Good news is that this is going to be a marathon series, so you won't wait for months until you see residue. Okay. So I set myself the goal to get to residue by the end of the month, but not today. Okay. And convex cone, I can't explain now. Do you also plan to cover linear programming and optimization down the road? Okay. Down the road. It's difficult to be a one-man department, if I do say so myself. You know, it's difficult to cover all these subjects, because yesterday I mentioned in our integral transform stream, you almost never see differential equations side by side with moment generating function. That is the topic from probability, central limit theorem, which in my opinion is a great shame due to compartmentalization, because the underlying idea is very much connected, deeply connected. Convolution comes from probability theory and also comes from differential equation. This is not just an arbitrary formula. Okay. Anyway, so because we're covering so many different things, it's difficult for me to say just pick any random topic and start a series. Okay. And right now I already have many loose ends. So unfortunately, linear programming and optimization, well, perhaps optimization, okay, some aspect of optimization like optimal control is something we already started and we do intend to continue, but perhaps linear programming will have to wait indefinitely. Okay. Anyway, so let's continue with this property. So you have negative p implies q. So let's calculate this column. This is true whenever the premise is false. So the first two rows is automatically true. And when negative p is true and q is true, that's the third row, you also get true. In the last case, you get false. And as we can see, these two columns are the same. So therefore, indeed, we have logical equivalence, and therefore you can prove P or Q by assuming not P and then prove Q. Intuitive, but this is the actual proof. Let's go. Proof. So assume z1, z2 is 0. That's just assuming the if part. And also let's assume one of the propositions z1 equals 0 and z1 and z2 equals 0 is true. And are false, okay? We want to negate one of them. If you assume one of them is true, then there's nothing left to be proved, of course. So let's assume z1 is non-zero. And we need to show z2 is 0. So z2 is 0. So to do so, we can take advantage of the fact that z1 is non-zero and therefore it has a multiplicative inverse. Okay, so we can write z2 as z2 times 1. And 1 can be written as z1 times z1 inverse. Okay, and then use associativity. You can write as z1, z2, z1 together times z1 inverse. But z2, z1 is the same as z1, z2, commutativity, and times z1 inverse. And z1, z2 is 0. So 0 times z1 inverse, so that's a 0, as needed. So we're done. So that's the property here. Okay. Anyway, okay, let's move on. So a quick corollary is if z1 and z2 are both non-zero, z1 times z2 is non-zero. The corollary, basically the contrapositive. Says the following: if z1 non-zero and z2 non-zero, then z1 times z2 is non-zero. Okay, easy. So now we say something about subtraction and division. So for subtraction, we can define it as such. Okay, anyway, let me defining subtraction. Subtraction z1 minus z2 is defined as z1 plus the additive inverse of z2. And division z1 over z2 is defined as z1 multiply z2 multiplicative inverse if z2 is non-zero. Okay. So now you can give the formulas for those. Okay. So here, this is equation 1 in this section, and this is equation 2 of this section. Okay. So formulas. Okay, z1 minus z2, this is x1, y1, ordered pair, plus minus x2 minus y2. Okay, this is x1 minus x2 y1 minus y2. Easy. Okay, and now let's do the division formula. So z1 over z2, this is z1 times z2 multiplicative inverse, which is, can write it as x plus iy, okay, times x1 plus iy1, sorry, x2 minus iy2 over x2 squared plus y2 squared. Okay, and yeah, and therefore we have the following, which is x1, x2 plus y1, y2 plus I x x2 y1 minus x1 y2 over x2 y1 minus x1 y, yeah, over x squared plus y squared. And these two are equations 3 and 4 in the main text. Okay, so the textbook uses here. This is also 3 and 5. Okay, 3 and 5, 6 and 4 and 6. So basically, in the textbook, the two equations are written in the order pair notations and then in I notation. So I won't repeat those. So because it's obvious, you can convert between the two notations. Okay, so we'll just move on. For the division formula, there is no need to memorize the formula. Okay, you can write division as such. Division formula alternative derivation. That's the multiplying conjugate trick. So z1 over z2 is as follows. So x1 plus iy1 over x2 plus iy2 is x1 plus iy1. Anyway, actually, it did remind me that because right now we're also doing elementary analysis, like the Zorich series, right? Once we have the fundamentals, like for example, when we discuss open and closed sets, that kind of thing, we can talk about convex analysis. Perhaps not convex optimization, but convex analysis, which is useful for machine learning. So yeah, we're going to multiply and divide by the conjugate of the denominator, which is x2 minus iy2. Okay, x2 minus iy2, and let's see what happens. They should be the same as earlier. Actually, I missed the 2 subscript here. My bad. This is x2 squared plus y2 squared at the bottom. x1 x2 plus y1 y2 plus I y1 x2 and then minus no worries, my pleasure, minus x1 y2. All right, so that's another way to arrive at the division formula. Okay, and of course you have the next property, which is also very much expected, z1 over z2 over z3. Okay, and this is z1 over z3 plus z2 over z3. And the proof is straightforward. So just use the definition of division. The left-hand side, by definition, is z1 plus z2 times the multiplicative inverse of z3. So you get, by the distributive law, z1 times z3 multiplicative inverse plus z2 times z3 multiplicative inverse, which is z1 over z3 plus z2 over z3. Okay, so there's that. Okay, so it's a simple property. Okay, and now let's take a look at some example. Just one example in the main text, and then we'll do some exercises. The example of this method earlier. Actually, let me put the example here so it fits directly with the method. With multiply by conjugate method here. So here we want to calculate 4 plus I over 2 minus 3i. And to do that, we multiply by conjugate on both top and bottom. 4 plus I times 2 plus 3i, 2 minus 3i, and then times 2 plus 3i. Okay, and then you get at the bottom, that's 2 squared plus 9 squared, 3 squared, okay, and then plus you get 8 plus 12i, and then plus 2i minus 3. Okay, so we get 5 plus 14i over 13. Yes, with Z3 non-zero. Yes, Z3 must be non-zero. Good call. Here, in the property, Z3 must be non-zero. You're right. Yeah. Otherwise, the multiplicative inverse does not exist. Okay. So there are still some more expected property that okay, there's some expected property. Let's actually, which one? Yeah, so more properties. 1 over z2 is the multiplicative inverse of z2. You say, whoa, what is this? Isn't this completely trivial? Yeah, it kind of is, because in the definition, if you set z1 in the definition 2 here, if you set z1 to be 1, that's exactly what you get. Okay? Indeed, set z1 equals 1 in 2, we get this. Okay? Simple property. So as a result, you can write z1 over z2 as z1 times 1 over z2. Oh, Guy Pirate says, I remember a multiplicative inverse formula geometrically. The argument have to cancel to 0. Yes. Yes. You know what? Right now we're not even discussing geometry yet. We'll get there. Yeah, this is correct. So the argument has to cancel to 0. So it has a negative argument. And then the magnitude also have to cancel. Exactly. Exactly. So it's not quite the inversion in the sense of geometry. Okay. In geometry, when you talk about inversion with respect to a circle, by the way, inversion geometry is a highly interesting technique or subfield of Euclidean geometry. Inversion geometry is pretty cool. But 1 over z is not quite inversion. It's like 1 over z bar. That would be the inversion geometry. Yes. Yeah, I think you mentioned z bar. Okay, correct. Yeah, glad someone mentioned it with the geometric meaning of inversion. It has something to do with the inversion geometry in Euclidean geometry, but slight distinction there. Okay. Hang on a second. Hang on a second. Somebody messaged me. It was quite important. Okay, sorry. This is an important message I need to respond to. My bad. Okay. I mean, I don't. I think I need to stop apologizing so much because this is real life. It's quite important. Okay. Sorry. I'm back. Yeah. So here we have the more properties which are mostly trivial, but let's list them regardless. This is equation 9, and this is equation 10. Okay. And also, of course, I will stop writing every time z2 not equal 0, okay? Because this is, it's just like in algebra. When you write 1 over x, it has a default domain, x non-zero. Okay. Okay, this is assumed. And here we have the next exercise. The next, it says, by observing that, it says also by observing you have by observing that z1, z2 times z1 inverse times z2 inverse equals z1 inverse times z2 inverse. Of course, this is just 1. Hence, the inverse of z1, z2 product is z1 inverse times z2 inverse, because it multiplies to 1. Okay? And one can use equation 9, yeah, this one, equation 9, to show that. So equation 9 implies 1 over z1 quantity times 1 over z2 quantity is z1 inverse, z2 inverse, which is here over here, z1, z2 inverse, which is 1 over z1, z2. Okay, nice. Another useful property to be derived in the exercise is the following. Okay, so this is 12 to be derived. This is 11. And the next one needs to be derived in exercises. It is z1 over z3 times z2 over z4 equals z1 z2 over z3 z4. Okay, this is 12. It will be derived in exercises. Okay, and finally we have the binomial formulas. The binomial formula is also left as an exercise. It is written as follows. So you have z1 plus z2 together raised to the nth power, which we also used yesterday to derive the moments of normal distribution, general normal distribution. N choose k times z1 to the k times z2 to the n minus k. And of course, because of commutativity, you can write the left-hand side as z2 plus z1. And apply the same expansion will give you n choose k, z2 to the k times z1 to the n minus k, where n choose k is n factorial over k factorial n minus k factorial. Okay. So there you go. So that's the main text for section 3. Okay, main text for section 3. The binomial formulas are also labeled. This is equation 13 and this is equation 14. Binomial formula. Okay. Now let's do the exercises. Okay, guys, I think what we did earlier was a good interjection, right? When we do the exercises in the previous part, we were talking about Hardy and Littlewood. I think as a break, we could talk about stories of mathematicians and history of mathematics. Just Wikipedia articles and the links there would give us plenty of material. Do you like the idea? Chat, let me know. Do you guys enjoy history of mathematics and stories of mathematicians? Okay, so I'm going to do some exercise and let's talk about, for example, the story of people who invented complex analysis. So it will be an interesting interjection instead of just doing intense math all the time and it gets tiresome. Okay, 1a. So we wanted to calculate a bunch of expression. 1 plus 2i over 3. Now for me, absolutely great, awesome. Let's do that. Okay, 1 plus 2i over 3 minus 4i, and then plus 2 minus i over 5i. Okay, so there are multiple ways to do this. Right? We can, I mean, it's up to you guys. We can choose which way. We can simplify each fraction, or we can combine them into a big fraction. Let's simplify each fraction. How about that? Because it feels simpler that way. Right? Because I was thinking, if you multiply the denominator to get a bigger fraction, the numbers gets higher, and then you need to multiply by a conjugate, which became kind of ugly. So let's just simplify each rationalize, or actually make the, not rationalize, but make the denominators real. Okay, 3 minus 4i times 3 plus 4i, 1 plus 2i times 3 plus 4i, plus 2 minus I over 5i, and then times minus 5i. Guys, actually, it reminds me of something in my in high school. So, guys, when you first learn about irrational numbers in high school, if you get, say, an expression like this, 1 over square root of 1 minus 1. If you see something like this in high school, do your teacher require you to rationalize the denominator by writing it this way? So our teacher was weird. If we simply leave it as such, we will lose mark. You have to do this and then get a you get a rational denominator. This is just square root of 2 plus 1. Do you guys have to do this? For me, I never really understood why this must be done. This is a completely valid expression. And not just this, like for example, if you do trigonometry and you write 1 over square root of 3, that's a special trig value. It has to be written in freaking square root of 3 over 3 to quote-unquote rationalize the denominator. I always felt like this is such a pointless exercise. Why do people do this? I suspect there is a valid reason back then, because the calculation of irrational numbers relies on tables. For example, you would have a table of common square roots. The thing is, it's much easier to divide by a whole number or a rational number than, say, divide by a rational number. This way you can just look up the value of square root of 3 and then divide by 3 using the tabulated value. But nowadays, who cares, right? But for some reason, we were required to, in high school, to do this. You can't leave an irrational on the denominator, which was very puzzling to me. Well, anyway, here we're basically kind of doing the same trick, right? Here you have 3 squared and plus 4 squared at the bottom. Expand the top, you get 3 plus 4i plus 6i minus 8. Okay, and here you have 25 at the bottom and minus 10i plus, actually minus 5, because it's a minus times minus and then I squared, so it's minus 5. Okay, so luckily the denominators match, 25. So on the left we have what? Minus 5 plus 10i minus 10i minus 5. So this is minus 10 over 25, which is minus 2 over 5. That's it. Okay, part B. Part B. Okay, 5i over 1 minus I times 2 minus I times 3 minus I. Okay, so why don't we simplify the denominator first to get just the x plus iy form and then decide what to do next. Okay, 5i over, here on the bottom, you get 2 minus 3i minus 1. Right, 2 minus, this is 2 minus 3i and then minus 1. Yeah, and then times 3 minus I. So this is 5i over 1 minus 3i times 3 minus I. Multiplication give us, so you get 3 minus 3i times minus I, that's a plus 3i squared, so that's a minus 3. Okay, and imaginary part, you get a minus I and minus 9i. So this is 5i over minus 10i, which is minus 1/2. Okay, this is part B. Part C. Let's keep going. 1 minus I to the 4th. So let's do 1 minus I squared and then squared. 1 minus I squared is 1 minus 2i plus I squared. Okay, which is just minus 2i. So minus 2i quantity squared is 4i squared, which is minus 4. Okay, simple exercise done. Okay, and 2, we want to show 1 over z is z. Okay, so let's go. Let's do that. Proof. How about this? Well, we need to look at the definitions. So 1 over z, 1 over z is here, according to property. Let's try to quote the property, okay? So that's 9. Using 9, this is the multiplicative inverse of 1 over z. Okay, this is a multiplicative inverse of 1 over z. And 1 over z is what? That's the multiplicative inverse of 1 over z. Once again, using 9. Kind of silly, but it's true. But the multiplicative inverse of multiplicative inverse is just z itself. Since z times z inverse is 1, and multiplicative inverse is unique, which we proved earlier. Okay, so that's done. Okay, that's 2. Easy. 3. 3, we need to show that z1, z2 quantity times z3, z4 quantity equals z1, z3 quantity times z2, z4 quantity. Okay, proof. Okay, so what's happening here? So we can do z1, z2 times z3, z4. So we want to combine z1 and z3. So we need to do associativity. We first need to do associativity. We want to say, how do we do that? We want to combine z1 and z3. So let's exchange z1 and z2. This is kind of reminds me of my little experience with abstract algebra. You just come up with rules to, use the rules to basically try to manipulate rules. It takes trial and error. So you need z1 and z3 together. So this step is just by commutativity here. And now let's use associativity. You get z2, z1, z3, z4. This is associativity. And now let's use commutativity again. Z1, Z3, and then Z2, Z4, which you can then use associativity to group Z2, Z4 together. Okay, awesome. So here, earlier, for we need to show that if Z1, Z2, Z3 is 0, then at least one of the factors is 0. So then Z1 is 0, Z2 is 0, or Z3 is 0. So that's the goal. Very similar to the opening proposition. Okay. Well, why don't we just use that property then? So assume Z1, Z2, Z3 is 0. Okay. So let's assume also Z1 not 0 and Z2 not 0. We need to show Z3 is 0. Okay. So yeah, since we have the corollary, by our corollary, the corollary of this section, there's only one corollary of this section. Z1 times Z2 is non-zero. Or by corollary of this section, Z1 times Z2 is non-zero. Okay, and since Z1, Z2 quantity times Z3 is 0 by the opening property, the first property, okay, Z3 is 0 as needed. Okay, so you see the exercises are very reasonable. Okay, it makes sure that you check the details in the main text. Nothing crazy so far. Okay, so that's the this exercise. The next exercise, we want to derive equation 6. Derive equation for the quotient by the method described just after. Well, we derived that here in exercise number 5 says derive this equation number 6, the division formula, using this method, which we did. So we're not going to do so. Okay. Exercise 5 is derive Z formula for Z1 over Z2 when using multiply and divide x2 minus iy2 and x2, yeah, divide, multiply and divide this. So this is already done earlier. Okay, so we can skip that. Exercise number 6. Exercise number 6. It says using equation 10 and 11. to show the following. To show z1 over z2 times z1 over z3 actually times z2 over z4 is z1 even z1 z2 over z3 z4. Okay, so what is 10 and 11? Let's put it down. Okay, so 10 says z1 over z2 is z1 times 1 over z2. Sorry, I may have missed your answer to my question earlier. Actually, sorry, like, Sha, it's my bad. I missed the chat for so long. So yes, just to answer your question in one sentence, I will start from the beginning because I have no idea how diffusion model works, even though I think I have some of the essential ingredients. I understand some of the essential ingredients like SDEs and Fokker-Planck, but not how, in terms of how they build diffusion model. And I definitely don't have experience with deep generative modeling. Okay, so I'm looking forward to learn it from scratch. There's also an MIT website, MIT ACW website, with Python notebook and stuff like that. But our focus is going to be on the mathematical foundation. There won't be any live coding there because, well, MIT already posted the code there. So I'll be spending most of the time just talking about the math. Okay, not talking about the math, actually. Talking about math is not what we do here on the channel, don't we? Right? Is not what we should do on the channel, do we? We actually want to show the inner working of math, not just talking about it. All right, awesome, let's go. So use 1011 to show this, and of course other familiar properties. Proof. z1 over z3 times z2 over z4. Okay, so this is z1 times 1 over z3, yeah, and then times z2 1 over z4, okay, and then you just use here we use 10, and then use actually here this is the first group, right? This is the second group. So we want to use this exercise. Basically, I want to put z1 and z3 together and z2 and z4 together. So this is exercise 3. We want to use exercise 3 and write, okay, this is the same as z1, z2 quantity times 1 over z3, 1 over z4 quantity. Okay. One of the great advantages of learning math beyond technical skills is it humbles you, theoretically speaking. It makes you realize you are never going to learn most of the math. Okay, it makes you appreciate your life. Just theoretically speaking. I know there are people who don't behave this way. There are certain math people that are very arrogant, but I don't know how they do it. But because for me, when I study math, it's crystal clear to me that my life is very short, and we should not waste time. Okay. Anyway, so here z1 times z2 times the second quantity. The quantity here can be I want to put it this yeah, so this is 11, right? This is 11. So using 11, this can be written as 1 over z3 z4, and now use 10 again, so you get z1 z2 over z3 z4. Okay, nice, awesome. 7 it says use the identity obtained in exercise 6. Use exercise 6, this exercise, to obtain the cancellation law. The cancellation law says, okay, z1 z over z2 z is z1 over z2. Okay, so let's do the proof here. Okay, so what is going on? So this looks like the right-hand side of exercise number 6. So let's write it this way. z1 times z over z2 times z. z2 times z. So this is, you can write it as z1 over z2 quantity times z over z by 6. This is exercise 6. And z over z, well, z over z, if we use, say, what's that? Yeah, z over z, let's use 10. This is z times 1 over z. Right? But of course, this is just 1, because you can write 1 over z as z multiplicative inverse. That's 9. So that's a 1, so therefore you get z1 over z2. Okay, nice. The last question is to prove binomial identity using induction. Prove binomial formula using induction. Okay. Proof. So the binomial formula, let's write that again. z1 plus z2 to the n. And we're going to quote the relevant properties as we go along. K goes from 0 to n choose k. Thank you very nicely. Oh, no worries. Anything in particular? Just thanking me for doing the stream or something else? Hi. Good morning. Actually, here is afternoon technically, but yeah. Have a good day. Let's prove it using induction. So let z1, z2 be complex numbers. Okay, we prove the formula by an induction on n. Start with the base case. Start with the base case. So yeah, this is another good practice. So basically, when you try, when you write proofs, okay, if you write English, write full sentence, or no English at all. It can be, say, just a pure deduction. If the question calls for that. But if you write sentence, write full sentence. If you write English, write full sentence. Okay? This is something that my professor of proofreading has taught me years ago. So for base case n equals 1, so the left hand side is just z1 plus z2 to the 1. Okay, on the right hand side, you have two terms. You have sum of k from 0 to 1. That's two terms. 1 choose k, z1 to the k, and z2 to the m minus k. So you have two terms, which is 1 choose 0, z to the 0, z1 to the 0, and z2 to the 1, plus 1 choose 1, z1 to the 1, z1 to the 1, and z2 to the 0. Okay, which is z2 plus z1 equals the left hand side. So base case is done. Okay, inductive case. With inductive case, let's assume. Okay, let's assume the formula holds for n equals k, where k is some natural number. All right. That is to say, we assume there exists a k in big N such that z1 plus z2 raised to the k. Actually, yeah, we should probably change the call it m. Okay? Change the index. K is the summation index. That's not good. Let's call it n equals m, where m is some natural number. Okay, z1 plus z2 to the m is the sum of k from 0 to little m. M choose k. Okay, z1 to the k times z2 to the m minus k. Assume this is true. We need to show this is true also for n equals m plus 1. Need to show I'm sure Athens people would prefer to fight Persian than this sort of marathon. If this is the marathon we do, there wouldn't be any war, would it? Right? So need to show this formula for n equals m plus 1. Okay, so let's do that. So the left hand side, z1 plus z2 raised to the m plus 1, of course this would be z1 plus z2. Let's call this the induction hypothesis, IH. z1 plus z2 to the m times z1 plus z2. Okay, and then we use the induction hypothesis so that this is the sum k from 0 to m, m choose k, z1 to the k, z2 to the m minus k. Actually, let me write it this way. It doesn't matter, but it saves me some bracket. Okay, so there's that. And then use the distributive law. The first z1, okay, the z1 times the sum gives us a new sum, which goes like the summation of k from 0, summation over k from 0 to n, m, and m choose k, z1 to the k plus 1, z2 to the m minus k, okay, and then plus the sum of k from 0 to m, m choose k, z1 to the k times z2 to the m plus 1 minus k. Okay, so what can we do now? What can we do now to simplify the situation? So we wish to look at our goal, right? We wanted the formula to hold true for m plus 1. So let's get our goal first. So we want something like this. We want the formula sum from 0 to m plus 1. And then m plus 1 choose k. M plus 1 choose k. And then z1 to the k. And z2 to the m plus 1 minus k. So that's what we wanted. This is what we want. So looking at this final goal, the second sum seems to have what we needed, right? You have m plus 1 minus k, so that's nice. And on the left, we can use a shift of index, right, to get m plus 1. So let's do a shift of index for the left sum. Let's leave the right sum unchanged. So we want to have a z1 to the k. So z1, k plus 1 is now k. And my brain always hurts when I do this sort of index shifting. I know, I suck. So let me just put k plus 1 equals L, okay? So this way I don't struggle nearly as much. Okay, so now we have a new summation index called L. So k here, k is L minus 1. K is L minus 1, so z2 would have power m minus k, which is m plus 1 minus L. And the coefficient, binomial coefficient, would be m, choose L minus 1. And the index L goes from 0, actually 1 to m minus 1. So that's the shifted index, index shifting for the first sum. And the second sum is unchanged, because we see the product in the second sum is the same as in our goal. We want that. So now we have, you can now rename L to K. So this way, the first sum also looks like the last one. Okay, and now we need to combine the two sums. But of course, we notice an issue here. The index range aren't the same. So we're going to single out, say, k equals 0 here, when k equals 0, the second sum will give us m choose 0 times z1 to the 0, z2 to the m minus 1, oh, actually, my bad. Here, this should not be m minus 1, it should be m plus 1. What am I doing? Yeah, you see, I always hate switching index because my brain hurts when I do that. So LK goes from, is that right though? Is that right though? So K is greater. Let me write an extra inequality because I really cannot do this sort of index changing. My goodness, I'm slow. So K is greater or equal to 0. Give me green pen, thank you very much. K greater or equal to 0, less than or equal to m. So K plus 1 is greater or equal to 1, less than or equal to m plus 1. Okay, I'm sure now. This is m plus 1. Thank goodness for that. Okay, so here we're isolating k equals 0 term into a separate one. So this way, the second sum now have index k go from 1 to m. So this is now the sum over k from 1 to m. Okay? Let's not write the general term yet, because the first term also has an extra term when L is m plus 1. So the last one, we have another term trailing behind, which is m choose m. Right? M choose m. z1 to the m plus 1, z2 to the 0. Okay, and in the middle you can combine the general term in the summation. This last problem is brutal. Well, I think it's okay. It's just this summation sign that looks a little bit ugly. Proving binomial theorem is still kind of a standard problem in algebra. Nothing we've seen so far is like ridiculous, you know. So this is definitely more sophisticated than the previous one, simply because of the summation notation. Okay, that's it. So now we can use a property of the binomial coefficients. Here, this is a property of the binomial coefficient. So basically, we have an identity. Let me write it on the side. Binomial coefficient, or this is the Pascal triangle. Pascal triangle. Actually, this should be called Yang-Hui triangle. Have you guys heard of that? Okay. And if not, you guys are about to receive some education. Okay, kidding, okay? Pascal triangle, because Yang Hui, Chinese mathematician, discovered like several centuries ago before Pascal did. Centuries ago, okay? So Pascal's triangle, history, also in India too. This is the Chinese Yang Hui's triangle. Yeah, so this is in Chinese literature of mathematics, this is always called Yang Hui triangle. Is it 1, 1, 1, 2? 1, 1, 1, 1, 2, 2, 1, 3, 3, 1, 1, 4. This is 4, this is 5 in ancient Chinese. Okay, so yeah, Yang Hui discovered it when? In the 13th century. Oh, I thought he was earlier. This is known as Yang Hui's triangle in China. So, well, Persians and the Hindu mathematician, well, actually second, third, or second century BC. Well, oh my goodness. Kudos to them. Kudos to them. In Italy, the Pascal's triangle is referred to as Tartaglia's triangle. Actually, Tartaglia was the first one who discovered. Actually, you know what? We'll do this later. This is an excellent piece of math history. We'll do that. We'll save the good stuff later. Okay, we'll finish that and talk about math history later. We'll finish the drudgery of induction proof. Okay, anyway, so the Pascal triangle identity says this. So m l minus 1, m choose l minus 1 plus, oh, actually, let me change it to k. Okay. M choose k minus 1 plus m choose k is m plus 1 choose k. Okay? So that's the key ingredient here. Some index mess is going on, huh? What's going on? Wendelin, I think it's fine, no? I think it's fine. So let me just re-explain this step and recheck this step. So this is k equals 1, k equals 0. Okay, this k equals 0 isolated as this term. And the last term is from this sum. Yeah, I just fixed it. Okay, yeah, thank you for noticing. This is L equals m plus 1. And these are the middle terms. So now, I think we have pretty much what we need. So to conform to the final form, let's write the first term as m plus 1 choose 0. Actually, there is messed up here. This is a plus sign. What am I doing? Sorry, guys. Z1 to the 0, Z2 to the m plus 1. Yeah, k from 0 to m plus 1. M plus 1 choose k. Z1 to the k. Z2 to the m plus 1. Minus k, and then plus m plus 1 choose m plus 1, z1 m plus 1 z2 to 0. Okay, so yeah, this is the new sum, and therefore this is true, right? For basically we prove the formula for m plus 1 as needed. So whenever we say something like claim, need, when it's done, proving it, we say as claimed, as needed. It's kind of nice, in my opinion. And therefore, finally, we say by the principle of mathematical induction, the binomial formula holds, basically. Z1 plus Z2 to the n is the sum of n choose k, Z1 to the k, Z2 to the m minus k. K goes from 0 to m, 0 to n, for all Z1, Z2 in a set of complex numbers, and for all n as integers, as natural numbers. Okay, so that's it. That's the end of the proof. And we can just briefly verify the Pascal triangle identity here as well. Quick proof. Okay, on the left hand side you got m factorial over k minus 1 factorial times m minus k plus 1 factorial, and then plus m factorial over k factorial m minus k factorial. Okay, and let's combine the fraction. Multiply k here. Multiply k, you get a k factorial at the bottom. On top, you get k times m factorial. And here, let's do m minus k plus 1 factorial. Here, you would have to multiply by, this is m factorial times an extra factor, which is m minus k plus 1. All right, so m factorial is a common factor, and then times m plus 1. That's exactly m plus 1 factorial. So this is just m plus 1 factorial over k factorial times m plus 1 minus k factorial. So that is m plus 1, choose k as needed, which is the right hand side. So this is okay. All right. So as promised, let's look at the history of Pascal's triangle. Right. So we all know what Pascal's triangle is. In much of the Western world, it is named after the French mathematician Pascal. Although other mathematicians studied a century before him in India, Persia, China, Germany, and Italy. Even in Europe, you see, even in Europe, why? You can say, oh, they just didn't know what's going on in India, Persia, and China, although I severely doubt it. But what about Germany and Italy? Why privileging France? You know, I have no idea. Okay, this is the history. The pattern of the number that forms Pascal's triangle was shown well before Pascal's time. In India, Pingala, the person, Indian poet and mathematician, Pingala, 3rd or 2nd century BC, wow, described a method of arranging two types of syllables to form metrics, to form meters. What is meter? Is that some kind of poem? It's a basic rhythmic structure of verse or lines in verses. Damn, bro. Of various lengths and counting them, as interpreted as elaborated by Pingala's 10th century commentator. His method of pyramidal expansion, okay, is equivalent to Pascal's triangle. 6th century Indian mathematician astronomer later described the recursive method for computing binomial coefficient that is mathematically equivalent to Pascal's triangle, although arranged in a different orientation. See, awesome. In Persia, also, it was discovered. And is this in France? This looks like in French. So the French did it this way. Okay. Not as a isosceles triangle, but this way. Also pretty cool visualization. So the binomial theorem was also discovered in Persia. The Yang Hui. This is typically how most of the time how this thing is referred to in Chinese mathematics books, called Yang Hui triangle. Okay, Europe. In Europe, it first appeared in 13th century. The naming system crediting system in math is kind of messed up. Okay. In Italy, the Pascal's triangle is referred to as Tartaglia. So Tartaglia is also a very famous person. I mean, he invented the cubic formula, and also Cardano. Those two had a beef because Tartaglia invented the cubic formula and wanted to keep it as a secret. But Cardano was pestering Tartaglia to give him the secret, and he gave in. And then he gave in on the condition that Cardano would not publish it. It's like a secret between them. But of course, later on, Cardano immediately published it, and now the formula is called Cardano formula. The cubic formula is called a Cardano formula. I guess you can say, for the sake of scientific progress, Cardano did the right thing. But at least name the person, we know what happened. At least name the formula after Tartaglia. Isn't that interesting? And by the way, Tartaglia was also arguably the world's first ballistician. Tartaglia was first to apply mathematics to the investigation of paths of cannonballs, known as ballistics. He did the work of ballistics before Newton had his Newton's law, and this was very much influenced by Aristotelian physics. Okay, even though it looked medieval by modern standard, for the time, this was still revolutionary work. Ballistics. So he was the world's first ballistician. Although, even though he was very productive, he had a difficult life. I think he had a difficult life. Yeah, he was born. What's going on? Nicola was born. I don't know this place. Who's Michel? The father? Murdered by robbers, and Niccolo, his two siblings and his mothers were left impoverished. So this must be his father. Oh wow, that's brutal. Niccolo experienced further tragedy in 1512 when King Louis XII's troops invaded his city. The militia, of his home city, defended the city for 7 days. When the French finally broke through, they took revenge by massacring. By the end of the battle, over 45,000 residents were killed. During the massacre, Niccolo and his family sought sanctuary in the local cathedral. Jesus. French soldiers entered the cathedral, and the soldiers sliced Niccolo's jaw. Jesus. So Tartaglia was a nickname. After this, he would never shave and grew a beard to camouflage his scars. God damn. That's insane, That's some childhood trauma right there. Okay, yeah. So, and also Cardano. Well, he was pretty prolific as well. I know Tartaglia guys from a Vertasian video. I see. Was it about a cubic formula and complex numbers? I don't know. Yeah, so he okay, nowadays is known as the Cardano-Tartaglia formula. Yeah, the cubic equation. Okay, anyway, an interesting piece of math history. Okay, I think now we can continue to do some more math. Next up, is section 4. We're going to talk about vectors and moduli. Vectors and moduli. So finally, geometric interpretation of complex numbers about time. Okay, it is natural, just call it combinatorial triangle. Although I knew about Tartaglia's work on it. Yeah, I agree. So, yeah, just like quadratic formula, nobody gets the credit, okay? Yeah, so this is the next section called vector and moduli. It is natural to associate any non-zero complex number, x plus iy, as a direct line segment, like this. So this is e equals x plus iy. And that's a vector. So we can simply say complex number z or point z or vector z synonymously. Okay. So there's that, and the sum would just be the vector sum. Because of how sum is defined, the definition is identical to vector sum in R2. The vector sum can be interpreted as a sum of complex numbers. So you can use complex numbers to do a lot of geometry, actually. Some highly non-trivial geometry, actually. Yeah. So, yeah, just this is as a honorable mention, I think. How many of you guys know about the Simpsons line? In classical Euclidean geometry, Simpson line. This is the Simpson line. So what it says is the following. Okay, you have an arbitrary triangle, okay, and the circle is, and here you have the circumcircle. Yeah, the circumcircle is uniquely defined by the triangle, and if you pick an arbitrary point P on that circumcircle, and you drop the foot and perpendicular on each side. If you don't have enough length, you can simply extend the side like this. So basically, N is the closest point on AB, on the line AB to P. M is the closest point on the line CB to P. And L is the closest point on AC to P. Those 3 points lie on the line. They are collinear. And that line is known as the Simpson's line. Okay, and there's a converse as well. If the 3 closest points on P on the 3 lines are collinear, and no 2 of the lines are parallel, then P lies on the circumcircle formed by the 3 lines. So that's pretty awesome. Actually, there was I posted a post some day ago. There was this channel recommended by one of my viewers called Levi, who is also a viewer of JC. He recommended this channel to me called Olympia Geometry Club. For example, this is a video on Simpson's line. This is in my, let me just gonna share this into chat as well. This is of course classic Euclidean geometry done according to the style of Euclid. This is Euclidean geometry a la Euclid. Classic stuff. But nowadays it is kind of obscure because how little Euclidean geometry actually is taught in school nowadays. Simpson's line, results like Simpson's line are considered highly advanced and it's barely mentioned. I think it is beautiful. And you can actually prove this using complex numbers and give the equation of the Simpson line using complex numbers. Yeah, this is a Simpson's line. There's many gems of classical Euclidean geometry like this one that are almost forgotten nowadays. Okay, and here there's actually this amazing visualization. If you see this, the animation speaks for itself. Um, the this is the envelope. The curve is the envelope called Steiner's deltoid. Look like a delta. How awesome is that? Just amazing. Okay, and so of course, using classical Euclidean geometry, you can just prove it by angle chasing. But complex number gives you the equation of the Simpson's line. And here's the paper. Freaking gone? Are you kidding me? Okay, let's search it. The article is gone. Are you cannot be serious. Oh, thankfully it's still here. Okay, yeah. So this is a proof using complex number. You can do a lot of geometry using complex numbers. Okay, I'll share it. Okay. Simpson's line using complex numbers. I'll put it in chat. Highly non-trivial. Yeah, synthetic geometry is not my thing, sadly, right? It's beautiful in its own way, but the thing is, it's not very generalizable, right? The method is highly restrictive. It does not generalize to modern geometry, so that's why perhaps the reason schools are starting to teach less and less of it. Actually, we might start a discussion video, a discussion live stream or video. Perhaps a live stream would be better for that matter because we need interaction. The thing is, whether to teach Euclidean geometry is a big controversy. Right? Try to follow Heron's formula for the area of a triangle and find it so hard to follow, never could have come up with such a thing. Right? Heron's formula is the area of a triangle in terms of its side length. I think you can prove it using the cosine's law. Right? You first write the area of a triangle as half AB sine C, and then express sine C as in terms of cosine, and then you use the cosine law for you can use the cosine law to write the cosine in terms of side length, and then just simplify, which can be quite messy, but that's the brute force method to get the Heron's formula. Right. But then again, that requires trigonometry. I'm not quite sure if that's purely Euclidean, you know. Purely Euclidean geometry has little to no calculations going on. But then again, I don't know a lot about synthetic geometry myself because I'm pretty much educated in coordinate geometry. All right, so there's that. Is teaching Euclidean geometry in high school controversial? It is not politically controversial, but it's a subject of ongoing pedagogical debate regarding how and to what extent it should be taught. There's a lot of debate, not controversial, but debated. Debated. Still debated. Means highly debated. You know, the thing is, it is a gateway to logical proof, and the thing is not just that, because it's because of results like this. It's highly unexpected. So this makes teaching proofs fun, in my opinion. It's not just a dry exercise of starting from the premise, you write there exists for all, oh my goodness, and you seem to prove a result that is not very satisfying. It's true but not very satisfying. But the thing is, these proofs requires real ingenuity. There are logical deduction for sure, but the results are also beautiful and non-trivial. Right? So, for example, you can, I guess, theoretically, you can teach induction in high school and, for example, tell students, show students how to prove the fundamental theorem of algebra. So, fundamental theorem, not algebra, arithmetic, prime factorization. Is that beautiful? I mean, I just found it meh. I don't know about you guys. This is more beautiful to me. Of course, that's a subjective thing, right? And you have visual intuition, unlike abstract algebra. Geometry allows students to physically see and construct the math they're working on. Foundations. The case against it, it's inefficient and fragmented, exactly. Synthetic geometry is computationally inferior to analytic geometry. But the thing is, analytic geometry using coordinate system is also restrictive in its own way. Many elementary results in Euclidean geometry is difficult to prove using coordinate geometry. Like, guys, I'm pretty sure you know this theorem, right? In a triangle, say if you have a bisector, angle bisector, then say the angle bisector AE, okay, AD. D is the intersection of the angle bisector of A with BC. So you would have BD over the ratio between BD and DC and CD as the same as BA over CA. This is very easy to prove using classic Euclidean geometry. You just construct a similar triangle. But it's very difficult to prove using coordinate geometry. The thing is, how do you set up the coordinate system? There's no natural way to set up the coordinate system. There's no symmetry here. Well, you may say, okay, I'll just put B at the origin. Then how do you write the equation line for AD? It's not easy. Angle bisection, the angle bisector doesn't have a clean equation. So this, I think I'm in this camp. I lament the fact that I didn't learn enough synthetic geometry in high school. Analytic geometry is not a substitute for synthetic geometry, at least as far as Euclidean geometry is concerned. I believe teaching vector algebra, these things are useful and for calculus and stuff, but if you're talking about logical proofs, then coordinate geometry is, I don't think is more efficient as far as Euclidean geometry is concerned. Because after all, you're still using, even in advanced STEM, you're still using Euclidean geometry fundamentally, unless you do really advanced stuff like general relativity. Artificial rigor. Note that the infamous two-column proof required in high school do not reflect how mathematicians write proof. Well, how mathematicians write proof, in most situations, I know it is discursive. It's like an essay. But theoretically, you can still dissect an essay into two-column proofs. You have a deduction and you have a justification. That's it. And this is how machines do proofs as well. This is not how mathematicians actually write proof, because for typographical reason, if you insist on doing two-column, it would be difficult to typeset and the book will be longer. That's not, the logical structure is still two-column, a step of deduction and a justification. Euclid's original axiom is not entirely rigorous, of course. Like, the thing is, none of the high school stuff is entirely rigorous. Do you teach the least upper bound principle in high school? You still do calculation with them. These are non-reasons. Opportunity cost, memorizing obscure triangle congruency theorems would be better spent on high utility modern subjects such as statistics, data science, or matrix algebra. once again, if you want to really teach these things, statistics is not really teachable, or say mathematical statistic or deductive, rigorous statistic is not really teachable unless you already have a foundation in calculus and linear algebra. These are by definition university subjects. So none of these are actual valid reasons, in my opinion. Okay, I feel very strongly about this. Yeah, but that is algebra, right? Gwendolyn, you said you're completely right. The method I just mentioned for proving the Heron's formula, I think it's here in Wikipedia, Heron's formula. I mentioned, we could use it to, we could derive it using the law of cosine. Yeah, so this was the method I was talking about. It's not synthetic, right? It's algebra. So actually, yeah, I lament the fact that I did not learn enough synthetic geometry in high school. Right? What we learned was a mix, inconsistent mix of coordinate methods and synthetic method. Just whichever is faster, is more convenient for a particular result, we use that method. So it's completely inconsistent. Of course, you don't have to choose. The point is you don't have to choose. Both are very effective in their own way. You could argue that the Euclidean method is intrinsic. After all, a main theme of modern geometry is the study of invariant. Right? Like the tensor calculus we've been hammering. In tensor calculus, we've been hammering the message that tensor calculus is the study of invariance. You want to introduce coordinates to facilitate calculation, but you don't want your result, like a derivative, to depend on the choice of coordinate system. That's why you have notions like the covariant derivatives. Right? Getting invariant is difficult. Euclidean geometry in a sense, is intrinsic. It works with invariant themselves, length, angles, area, that kind of thing. And eventually, of course, you always need a coordinate system to do calculus. But the thing is, I don't know, I just feel very strongly about this. None of these reasons seems very valid. First of all, there is no definitive advantage of analytic geometry over synthetic geometry in proving many of the Euclidean geometry results. Of course, vector and complex arithmetics are more useful, but the thing is, are we talking about logical proofs, or are we talking about rushing to calculus? Right. This is not artificial rigor. This is not artificial. It is completely rigorous by high school standard. Okay, unless you're introducing the modern standard of rigor from day one, then this reason is invalid. Abstract algebra should be paired with geometry before a unit circle. I agree. Abstract algebra, I mean, I'm not expert in abstract algebra, but abstract algebra, like for example group theory, is a formalization of symmetry. Even a novice like me can say that. And what better way to teach symmetry with geometry? Right? This way you will see abstract algebra allows you to do geometry more efficiently, not as an arbitrary abstraction, right? And the thing is, memorizing obscure triangular theorem, the problem is the obscurity is a completely non-objective standard. You could argue that certain theorems in real analysis are also obscure. Like, what is this? To do deduction, you always need to accumulate result, not in terms of mechanical memorization, okay? Not mechanical, but internalization. The thing is, no one can do math completely, you can, but no one realistically do math completely from scratch. You don't always start from the axiom, right? even in advanced math, we have convenient theorems like fundamental theorem of calculus. Right? Do you call that? Would you call that memorization every time you use a Newton-Leibniz formula? And statistic data science and matrix algebra are perhaps matrix. You can make a case that matrix algebra or vector algebra should be introduced to high school and can be introduced to high school. But rigorous statistics and data science are fundamentally college and university level subjects. You cannot discuss those things rigorously, even at a non-measure theoretic level without background in calculus. How do you discuss things like random variables without random variable distribution, expectation, things like that, without calculus? I guess you can theoretically, but without calculus, you can only deal with very limited scenario. Number theory when? Probably never. Well, that's not fair. Perhaps we will, in the introduction to proof theory, I did promise we will do number theory. Do some elementary number theory. This is the slides I made. So here. So I was doing an intro to proof bridge course, mostly with the goal of guiding beginners to analysis. But I did promise we will do some basic number theory. Things like divisibility, Euclidean algorithm, fundamental theorem, arithmetic, congruence class, to serve as illustrations for things like the equivalence relation, but not as a means, not as a goal to its end. Okay, we're not going to do number theory for the sake of number theory, simply because we have priorities on the channel. I mean, this is mostly applied math channel. Well, you could argue that cryptography is applied math. It certainly is, but it's beyond my expertise, and I have so many other things currently to do and to finish. So no serious course on number theory. Okay, not in any time soon. So yeah, guys, let me know what you think. I know probably I just started a flame war. Traditional Euclidean geometry definitely has a place in high school curricula. That's my opinion. Right? It makes math fun. Like, I don't know, like perhaps you guys think like just has different taste, and that's totally okay. Why don't you take much better books like J. Cumming Real Analysis and Spivak? J. Cumming analysis is for self-study, okay? It's for self-study. It's if I cover it, it will be like reading the entire book verbatim. And what's my point? And actually, you can go to J. Cummings' website. J. Cummings' book, not book, but he has a YouTube channel too. Yeah, I don't know if I've ever shared his channel, but you can. J. Cummings. It's a good book, but I'm not going to cover it because it is completely self-contained, and there's little thing else I could say. Okay, this is long form. I know this one. I have that. For Spivak, as far as Spivak is concerned, Spivak Calculus 1 is actually very close, so to say, in spirit to Zorich. Spivak 1, Spivak Calculus is very similar to Zorich. But I think on this channel I wanted to give more exposition to, say, underrated math book like Zorich Analysis. This is a highly regarded text because it blends calculus with analysis seamlessly. Okay, and this is what we're going to do. But we're going to do Rudin. Okay, I think after we finished Zorich chapter 3, here we're in section 3.13. So after we finish chapter 3 in Zorich, we will do chapter 2 in Rudin. Okay, so there's that. Okay, everyone has their own preference. I know. So like, this is an introduction to proof, towards analysis. And yeah, give it a shot. See how you like Zorich. Geometry makes you do creative things like while doing math, and visualization gives is so good. I know, right? I cannot imagine like if I don't do geometry at all, I probably end up hating mathematics. Let's be honest. Because a little bit of a personal story. When I was little in school, I kept making silly mistakes. Okay, I kept making silly mistakes, and I just hated that. I hated myself I just could not physically stop making silly mistakes. And I subscribe to the popular narrative that you're either a math person or you don't. Math person are those who somehow just don't make silly mistakes. Like my mom, she was a math person, even though she was not a mathematician professionally. So my mom, she was a she is, okay, she's still alive. She's a chemist. But her accuracy of mental calculation is so impressive, because every time I go grocery shopping with her, she mentally calculates the total cost in her head, and she could always spot whether the cashier make a mistake. I couldn't do that to this day. The speed and accuracy of her mental calculation was so greater than me. So I figured, oh, she was a math person and I'm not, until I discovered geometry. So even in my limited exposure to classical Euclidean geometry, made me convinced me that math is worth doing. Because this nice thing is, once you found a proof in geometry, that's it. There's no room for silly mistakes. You can still make logical errors, which is a different kind of error than stupid algebra mistakes. I figured that actually made me learn something. So that was my change of heart when it comes to mathematics. So geometry changed me when it comes to the opinion on math. And then in high school, I learned about classical mechanics, and of course, how math is applied and connected to the real world. So I was totally sold. So classical mechanics and geometry were my second and first love when it comes to applied mathematics. So I don't know about you guys. Of course, once again, I'm not trying to impose my view. It's just a personal story, okay? That's what convinced me that math is worth doing. Okay. I think you should not follow any particular book, rather take best from all books. No, I'm not going to do from cover to cover. Okay, I'm not going to do from cover to cover. And to be honest, okay, ideally I would be taking quote unquote the best from all books, but the thing is I haven't read many. That's the issue. For analysis, I've only read two. Okay, seriously. For analysis, I only read two. One is Abbott, one is Rudin. Even Zorich is new to me. But I have a very good impression of Zorich that convinced me that it's worth doing. Okay, I'll just put it this way. I'm not a library. Right now, for example, we're doing complex analysis by Brown and Churchill. Once again, you might argue this is not the best, but this is the one I'm familiar with. Simple as that. Okay, and we also have like a Russian-style complex analysis text by Mark Kushevich, just 3 volumes, over 1,000 pages, and I like it a lot because I was able to find many obscure results from it. Obscure, by math standard, I guess. So, yeah, definitely we'll jump around a little bit. For example, I said after we finish the chapter 3 in Zorich, we'll come to Rudin, because Rudin's exposition on basic topology, in my opinion, is still unrivaled. They need to do some number theory in calculus. No teacher could tell me how E worked. I'm not sure how E belongs to number theory, right? And to be honest, it's difficult to introduce E rigorously in calculus. And actually, guys, we were almost at introducing E. So this was this was actually, did I? Oh, it's here. It's this one. Yeah. So it was just a few days ago. Yeah, we were talking about E, and we were going to show why this limit exists. And after showing this limit exists, we're going to call that E. All right. So that's the kind of the our so there's a trajectory right now. We just proved a lemma called Bernoulli's inequality, and we'll use that to prove the sequence is monotone and then bounded. So by the monotone sequence theorem, the limit exists, and the limit is called E. It's very difficult to say that story rigorously in high school. Tell that story rigorously in high school. But still, you can say something like, because high school teaches derivative, right? High school teaches derivative. We know the exponential function. You can tell a high school student that the exponential function has a special property, that its derivative is proportional to itself. And the proportionality constant is exactly 1 if the base is E. And we're just going to call that E. Right? That's also rigorous. That's also rigorous without getting into the super fine details of real analysis, right? So this is still very intuitive, very computational, geometric, but not super, without turning high school calculus into real analysis. No, it's not, sorry, don't be sorry for ranting. I was ranting the whole time, like, while I was considered good at math when I was young, geometry was my weakest point, but I still love it. You could see math, exactly. Later, when I learned that they do it without the numbers we know now, was incredible thought. Yeah, exactly. I know I went to an art school, but they also try to give us insight into primes. I see. There's actually, geometry that are inspired by math. Projective geometry was inspired. Sorry, art. Math comes from art. Projective geometry came from art. Do you like solving Olympiad problem? I don't know. I'm pretty much indifferent about them. Sorry. Yeah, perhaps I said that on the channel earlier. Is that I don't really do. This is a very low priority of the channel. Olympiad problem is because we mostly do applied mathematics, and a lot of the modeling stuff, which I found interesting, is not covered in. Of course, nowadays you have more. You have more modeling contests. Perhaps we'll take a look at those too. But basically, the stuff I'm interested in don't have a lot of say overlap with Olympiad stuff. Okay. That being said, like, don't let that stop you or anybody else enjoying Olympiad stuff. I think there are fun problems, they're challenging problems, and I like problems that tells a particular concept, that motivates a particular concept. Okay, so that's kind of my thing. So is your real analysis course beginner friendly, like those who know calculus and for all the other stuff at high school level? So I think, if I have to do a self-assessment, okay? So for example, if we take a look at the Zorid sessions we did, a common recurring feature is we always go back to the basics, like how do you construct a proof? How do you negate a statement? And these are aimed at beginners, people who have little experience with working with, say, this kind of heavily mixed quantified statement. We spend a lot of time on those. And we try to give motivation of how to discover a proof, the scratch work. We show the scratch work. Actually, the book by J. Cummings is awesome because the one you mentioned is awesome because it also shows scratch work. That's why it's called the long format book, right? But that's a little bit of a rarity, in my opinion. For beginners, they're more interested in perhaps saying, okay, this is my target audience in mind. People who have more general STEM background, say people who came from physics, who came from computer science, engineering, and now they wish to learn the math foundation of their fields of interest, but they never have taken a proof-based math course. Like, for example, they have taken the standard calculus, standard linear algebra that are mostly computations without formal proofs. And now they, for example, need to try to understand financial math, try to understand advanced statistics and machine learning. Without a formal proof background, they can be difficult. I'm trying to bridge that gap. Okay, so the intro to analysis is aimed at that objective. Okay, people who have some STEM background, but not necessarily math major, and no background in formal proofs. And my objective is rather, so to say, is rather, say, specific. So to guide those people, beginner not in science, not in higher math, but in proofs in particular, proof-based math in particular. And I think real analysis is a good proving ground, right? So this way it bridges the more slow-paced intro to proof class and straight into like quote-unquote mathy math. Okay. Anyway. Okay, I hope that's a good, not good perhaps from your point of view, but at least I try to clarify my philosophy and stuff. A real number is a scam given every real number can be represented by a sum of complex root of unity. Kronecker-Weber theorem. Well, but real numbers are definitely not a scam. Period. Okay, you can have, say, a dispute over the foundation of that theory, which then have implications over the real. I don't know. Actually, I don't know much about an algebraic number theory, but certainly it did not disqualify real numbers. Okay, I don't know the detail of this theorem. Yeah, I'll be completely honest, but. Real numbers aren't scam, period. Okay. So, yeah, so here we're doing pre-complex analysis. You can call it this way. It's like pre-calculus, but for complex stuff. We're still doing complex algebra. Complex analysis really starts at the very last section where we introduce regions on the complex plane, where we discuss open, closed set, accumulation points. This is where the analysis stuff begins. Okay, so here we're doing actually pre-complex analysis. Okay, pre-analysis, just complex algebra right now. Okay, I think that's a good break. Let's come back and discuss complex numbers and their geometric meaning. Okay, standard stuff. Okay, no controversy. Oops, my screen went back. Yeah, okay. So no controversy. Okay, this is just standard material. No personal philosophy added in there. Okay, because if I just talk about the standard stuff, nobody will keep watching, right? Okay, no, I'm just kidding. Yeah. It's just okay. Everybody wanted to add some spice into the content. I think N.J. Wahlberger is Ivy League educated. Yeah, he is. He is. He does not. Yeah, he just of course I know. You can see my comment. If you go to his website, if you go to some of his video, you will see my comment. He does not believe in real numbers, like that he can do his own thing. Right. It's not like I think over the years he has gotten a little bit conspiratorial, like people try to put him down or something. Like, but I think that's just too much. But let me put it this way, okay? Let me put it this way. This is not a personal opinion. Constructive mathematics in general, or finitism, whatever you want to call them, has little to zero impact in applied mathematics. Okay? I'm a practical person. Okay? I try to bridge the gap between scientific applications and theoretical studies. This is one of my meta goals of the channel. But I really struggle to find any impact of constructive mathematics in applied field. Like, for example, he called the fundamental theorem of algebra a scam. Okay, now we'll say, well, in practice, we need to find roots for polynomial. If that's a scam, what's your alternative then? Okay, if let's say if your philosophy doesn't help me solve problems, I'm not interested. Okay, I'll be as honest as that. Okay, it might sound a little bit unromantic or even arrogant, but this is the way it is. Like, how is your mathematics, so how is your philosophy of mathematics going to help me? I think it's a natural question to ask. I just don't see the answer, unfortunately. Anyway, let's continue. So here we're going to introduce a few more notions called the modulus. Modulus, as well as conjugate. I think modulus, yeah, just for modulus in this section. So modulus is just the length of a vector, basically. The modulus of z, which generalizes the absolute value, is defined as x squared plus y squared, taking square root. Okay, just the classic Euclidean length. Okay, and now you can, this is equation 1. And of course, this can be written as the square root of the real part of z squared plus the imaginary part of z squared. Okay, so there's that. You have equation 1 and 2. Equation 1 and 2, and now we have the inequalities. Immediately you have the inequalities, which we might want to call it the right triangle inequality, but perhaps this is too trivial to have a name. So this is a real part of z, this is the imaginary part of z. Basically it says the hypotenuse is greater than either of the two legs. Okay, that's it. Okay. I'm looking for a channel who teach pure math. Well, perhaps this is not the right one for you. Although we do cover things like measure theory, it has no immediate application, but it's still geared towards probability. But like, if you're interested in pure math, awesome, that's awesome. It's just that on the channel, we tend to focus on the more applied stuff. Okay, so this is the identity of the channel. For the pure math, I mean, there's big names out there. I don't need to mention them, but definitely in my student years, I watched Michael Penn a lot. Yeah, that's a great channel for pure math. Okay, so there we go. We have the anyway, we have the right triangle inequality. Real part of z is less than or equal to the absolute value of the real part of z, and less than or equal to the absolute value of z. Imaginary part of z is less than or equal to the imaginary part of z taking absolute value, and is less than or equal to the modulus of z. So together, these are called 3. These are called 3, okay? Okay, and so actually, X, before you unsubscribe, or maybe you're not even subscribed, before you leave the channel for good, but because you mentioned Spivak, right? And we were doing tensors, and I commented in one of my video that we wanted to do tensors both the indices way and the more modern coordinate-free way, because we really wanted to understand both the classic literature and modern literature, because classic literature still dominate applied fields. For that, I'm going to use, for the index-free stuff, I'm going to use calculus on manifolds by Spivak. Okay. So calculus on manifold by Spivak, not the big calculus. Okay, calculus on manifold by Spivak is a very thin, very short book, and it's also a classic. And I think it's great for the coordinate-free stuff. Okay. Anyway, so that's another simple inequality, right? So you have the, of course, in general, you cannot compare complex numbers. You cannot compare complex number. Let me just put it that. Remark: complex number is not an ordered field. Complex number is not an ordered field. It can be an ordered set. You can put an order on it, but it won't be compatible with the arithmetic operation. It's not an ordered field. Okay, and should we show it? I think we should show it. Yes, I mean, Norman Wahlberger, he has good geometry video. That's true. That's true. Yeah, I just tend to ignore his opinions on infinity, on real numbers. I just don't find them to be very informative, or don't actually know what he's talking about and what is the exact problem with those. But his geometry videos are good. Yeah. Yeah. So credit where credit due, you know. So complex number is not an ordered field. Why? Perhaps this will take a little bit long to explain because we need to list all the definitions. And let me just grab my Rudin to get that, because it's not in Brown and Churchill. I think this is important. We need to emphasize what this actually means, because sometimes you often hear, oh, complex numbers cannot have an order, which is not strictly true. The thing is, a complex number is not, it can be an ordered set. You can put an order on it, and the order can even satisfy the least upper bound principle. Yeah, but it's not an ordered field. Okay, let me grab Principle of Mathematics by Rudin. So the proof is actually very easy, but you need to list all the definitions to say what exactly do we mean. Okay, so this is what we mean. And this is not in the Brown and Churchill book, so I'll put it a different color. Okay, so I think this is, although this might slow down our progress a bit, but this has to be secured, because it's not a dogmatic thing. Okay, you cannot put an order. You can, but it won't be compatible with the arithmetic operation. That is what it's about. Okay, so I'll just put it this way. So the so C PMA, Principle of Mathematical Analysis by Rudin, Chapter 1. Chapter 1, exercise or problems, is it called problems or exercise? Yeah, exercises. Exercises 8 and 9. Exercise 8 says the following. Prove that no order can be defined in the complex field that turns it into an ordered field. No order can be defined in the complex field in C, okay, that turns it into an ordered field. This cannot happen. And Rudin gave a hint. -1 is a square. Is a square in C. Okay, so that's 8. And 9 is a clarification. It's not that no order can be defined at all. You can, and it can even behave nicely, but it won't be compatible with the field operations. Okay, 9 says the following. It says, suppose you have z equals a plus bi, and w equals c plus di. Okay, so define, here's the definition. Define z is less than w. Okay, this is the new notion, if the custom made for this exercise. If a is less than c, and also, okay, I'm using exact wording by Rudin. If a is equal to c, but b is less than d. It's like a dictionary. So if the two first letters agree, right, then you can order them by comparing the second letter. B is less than D. Okay, this is called a dictionary order or lexicographic order, for obvious reason. Dictionary order. And it is obvious that you can generalize this order to any n-tuple, not just ordered pair. Okay, so there's that. We want to prove, you can prove this. I'm not going to do all of these exercises. I'm just stating the results, okay? The key message is that you can turn the set of complex numbers into an ordered set. C is an ordered set. With this definition, with the notion of less than. Okay, so we need to give meaning to these notions. Ordered field, ordered set. Okay, so let's start with ordered set first. Okay. So ordered set is as follows. Definition 1.5 in Rudin, PMA. Yeah, it takes a little bit of the time to do the definition. PMA 1.5 definition. Here's a S is a set, and order on S is a relation. Right? This is the kind of problem that beginners run into. Say, if you don't have formal proof writing background, and let's say you try to read Rudin, okay? Let's say, consider a person who has taken and aced standard calculation-based calculus and linear algebra, and now try to read Rudin. He or she is unlikely to suspect that the relation has a special meaning in mathematics. Relation is a technical term. Right? Because relation is not defined in Rudin. Relation is what? Relation is a subset of S times S. But this is the sort of thing that beginner tends to not know, right? So that's why I'm doing things like, see, set theory, equivalence relation. Not just equivalence relation, but also relations in general. Function is a relation, right? Less than is a relation. Equivalence relation, of course, there are relations. Anyway, so let me save that. Okay, here, this is a relation denoted as less than, such that you have the following property, such that you have 1, 2, 3. Actually, 1, 2. 1, 2. So it says if x is in S and y is in S, then you have one and only one statement true. Exactly one of the following true. This is called the trichotomy property. X less than y, x equals y, or x is greater than y. This is called the trichotomy. Okay? Okay. And next up we have the property called transitivity. These are expected property. And now we're just defining the relation abstractly, axiomatically. If we satisfy these two properties, we call it an order, according to Rudin. So you have for all, that's right, for all. Okay, if x is less than y and y is less than z, then x is less than z. I think this is a natural requirement. You have transitivity between elements. So this is an order. Okay. An ordered set is simply a set with an order. That's definition 1.6. An ordered set is a set S in which an order is defined. So exercise 9 says you can find, actually exercise 9 says this dictionary order, aka lexicographic order, satisfies 1 and 2. So that's what exercise 9 is about. You need to verify 1 and 2, which we will not do here because that's not terribly relevant to complex analysis, but this can be done. Okay, that's the proposition here. Is defined. What we are going to do is 8, exercise 8. It is not an ordered field. So what is an ordered field then? Well, we first need to define a field, and that's 1.112 definition. So field has two operations. F has two operations, is addition and multiplication. So together this is a field. If the following true. Okay, if the following true. So that's the field axioms. So first, this is transitivity, trichotomy. Okay, transitivity. Okay, ordered set. Okay, this is a field. Let's define field. Field, you have the field axioms. So addition axiom A1, this is closure. So if x and y are in F, for all x and y in F, we have all x and y in F, we have x plus y is in F. So that's the closure property of addition. A2 says addition is commutative. Okay, x plus y equals y plus x. Okay, A3 says associativity for addition is true, x plus y. So basically complex number is a field. Okay, x plus y plus z is x plus y and then plus z. Associativity. A4, existence of 0. There exists 0 in F such that you have the property that x plus 0 is always x. It existence of 0. And A5 says the following. There exists, says the following. For every x in F, there exists a 0. Okay, there exists, not a 0, there exists an element which we call minus x in F such that x plus minus x is 0. Okay, so that's the addition axiom, totally expected. And now you have the multiplication axiom, which very much parallels the situation in addition. Says for all xy in F, x times y is in F. Okay, M2 multiplication axiom number 2 says x times y equals y times x. M3 associativity says x times y quantity times z equals x times y times z. M4 is existence of 1. There exists an element called 1, which is non-zero. Okay, 1. We assume 1 is non-zero, and for every x, for every x, here I'm just going to write 1 times x equals. This is not completely formal. Because here, just like in A4, I should write for every x. And in A2 and A3, I should write for every xy, for every xyz. Okay, I'm skipping those. I think this is understandable. Okay, and M5, there for every x in for every x non-zero in F, for every x, you just say every, this is awkward, non-zero x in F, every non-zero in F, then we have what? We have there exists this element called x inverse in F such that x times x inverse is 1. Okay. Yeah. So that's the. Oh, actually, there's one more. The distributive law, D. D says x times y plus z is xy plus xz. This tells us how addition and multiplication interact. Okay. This is a field axiom. And now you have field. You can talk about ordered field. But the thing is, ordered field is not simply a field with an order. There are additional requirements, and that's actually what breaks. That's what forbids complex numbers to be an ordered field. So this is definition 1.17 in Rudin, which says an ordered field. Okay, I want to do this once and for all because later on this will probably also be used in other videos and streams. So I want to just put it down in a nice collection here. An ordered field is a field F which is also an ordered set and with two additional properties. Okay, this is Rudin's introduction. There are other ways to introduce ordered field. For example, you can introduce field first and then define what is a positive, what are the quote-unquote positive elements in there. Axler does that. Yes, field also have distributive property on the right. Yes, you're right, because you already have commutativity. M2 and D together implies distributivity on the right. Right? Multiplication is commutative. That's immediate. Okay, so ordered field is a field which is also an ordered set. Yes, it does not matter because multiplication commutes exactly for that reason. Very nice. So one says such that you have two additional properties, which is x plus y less than x plus z if y is less than z. It's like we do this all the time, right? We add the same thing on both sides and the inequality sign holds true. Okay? So second says because it is an ordered set, right, you can compare elements with zero. Right? So it says let me just perhaps put the assumptions here is up front is better, it's more natural, okay? Slightly change the wording in rooting. So if y is less than z, then x plus y is less than x plus z. So that's another axiom for ordered field. Okay, additional axiom number 2 says if x and y are both positive, okay, then x times y must be positive. This actually seals the deal. Rudin's hint is that -1 is a square. -1 is a square. So how can we do exercise number 8? Rudin PMA, exercise number 8. Proof. We assume there is an order on C. There exists an order called less than on C such that C is an ordered field. Then we have a trichotomy scenario. So let's consider I. Consider I, the number I. There's 3 cases. Exactly one must be true. I less than 0, I equals 0, or I greater than 0. I equals 0, obviously this is not true. This is clearly false, since I is 0, 1. 0 in a complex set is 0, 0. They're not the same. Okay, this cannot be equal. So you only have 2 cases to consider. So case 1, I is less than 0. So if I is less than 0, then what happens? There is a property, okay, from the ordered field. Okay, actually, perhaps I should add it here. There is a bunch of properties of Rudin proved. I'm going to use it here. Here, 1.17. 1.17 is a definition. 1.1 is a proposition. Proposition that says the following are true in every ordered field. the following true. So this is what happens. So you have, say, if x is positive, okay, then minus a is negative. Then minus x is negative, and vice versa. Okay. Yeah. Let's just write the whole thing. This is part A, part B. I probably don't need all of them, but just for completeness sake. No. So none of these are surprising, but they can be deduced from the axiom. That's the main point. Okay, y is less than z, then you can multiply x on both sides. Oh, sorry. If x is greater than 0 and y is less than z, then you have xy less than xz. Okay, this is part B. And then part C, you have if x is negative and you have the inequality y is less than z, then you have xy greater than xz. So multiplying a negative on the inequality flips the inequality sign. Okay. Property of the ordered field. So if x is non-zero, then x squared is positive. This seals the deal. In particular, one is greater than 0. See, this is immediate. Because I is not 0, therefore I squared is positive. I squared is minus 1. So that's the contradiction. Okay? Perhaps we should spend some time try to prove D. Huh? Let's try to prove D. Okay, we'll prove D, and then finally there's E, part E. Part E. For completeness sake, let's write the entire proposition down. So if 0 is less than x, less than y, then taking the reciprocal give us 0 is less than 1 over y less than 1 over x. Okay. What matters is D. This is the thing that makes complex numbers a non-ordered field. So here, I is not 1, so just use the trichotomy. You know I is not 1. And therefore by 1.18d, I squared is greater than 1, but that's a contradiction. Therefore by 1.18d, I squared is greater than 0. Namely, minus 1 is greater than 0. Minus 1 is positive, a contradiction. So this is why C cannot be an ordered field. The proof is very short, as promised, but writing those definitions down is not fun. Okay, so let's take a look at the proof of D, actually, because this is quite important. Proof of D. So proof of D goes like this. But you consider two cases, right? Because x is non-zero, then you have two cases. Case x positive. When x is positive, well, use this by 1.17 part 2. 1.17 part 2, you get x squared is positive. So we're done. Okay, then you just look at the second case. When x is negative, then what happened? When x is negative by A, then minus x is positive. So minus x is positive, therefore minus x squared is positive, which means x squared is positive. So earlier in the theory about fields, you can prove minus x squared equals x squared. So minus minus gives positive. Oh, hi Josh, thanks very much for joining the stream. So yeah, so that's part B, part D. Once again, not very long. The proof is much shorter than the definition, which doesn't happen very often in math. Okay, usually it's the proof that's difficult. So basically, that's the reason. Okay, be careful to distinguish an ordered field and an ordered set. Anyone up here? What do you mean? I'm here. What do you mean? People in chat? Looks to me there are 11 people in chat. On watching. Okay. Okay. Hang on. Let me just check whether my hang on a second. Let me. Okay. Awesome. I thought I have to leave earlier, so I messaged someone to confirm, but right now I'm safe for the rest of the day. Okay, I'm free for the rest of the day. Okay. Yeah. So, okay. So that's the explanation, full explanation of why complex number is not an ordered field. Okay, it's kind of glossed over in Brian Churchill that says you simply cannot compare complex number. Right. This seems to come up in discussion a lot. You cannot compare complex number. It's not that you cannot intrinsically impose an order. It's that no order can be defined so that it turns into an ordered field. Okay. Very important difference. Okay, so now with the notion of length, you can define distance. So distance between two complex numbers is just a Euclidean distance. Distance, let's say d of z1 and z2. This is the modulus of z1 minus z2, like this. Or you can write it in coordinate form, which is just the familiar distance formula from high school. On the plane, x1 minus x2 quantity squared plus y1 minus y2 quantity squared. Okay? And of course, you can draw the picture to accompany the formula. This is x1, x2, x1, y1, and x2, y2. Okay. Hang on. More message. Okay, I'll wait for that person to respond. I'm sorry. Okay, this is an important personal matter. I hope I can do longer today so I can finish chapter 1 today. But something in life is just more important even than math, you know. So, you know, to do math you need a lot of time, which is a luxury. You know, it's not like I will never say, okay, I'll just put it this way. I'll never judge a person because he have other priorities in life higher than math. I will never do that. But I will definitely do not buy the excuse that I'm not a math person, and it is okay. And I failed to win the genetic lottery. This is an excuse I will politely but refuse to accept. Okay. Okay. So it looks like I have to go in an hour. Okay, I have to go in an hour, which is a bit of a shame. So yeah, turns out I can recommend a stream of video that can be used to prove technique like this. Only did computational stuff. Okay, great. So actually, I have the playlist. So introduction to proof and analysis. So let me just hang on. Go to my channel, and I'll give the link there. Okay, it is still ongoing. Like, if you wanted to say clarify your goal a little bit, say what do you say? What is your goal when it comes to proof writing mathematics? Is it general? Or are you you said you've done computational stuff, so are you looking into particular field literature where the material there is kind of proof heavy and you find it difficult to get used to? Is that something that that sounds like your experience? But it's okay if you need more time to clarify that. Okay, you can always drop into my Discord server and to discuss your specific need. Okay, hang on a second.
Okay, so
sorry.
This really is a fascinating.
Damn it! I just want to share the playlist. How can I do that? Okay, so now I have a new playlist on my channel called Introduction to Proof and Analysis. I apologize, I haven't been sorting things out as promptly as I should have. But this playlist is my intro to proof and analysis. Okay, intro to proof, and you can think of it as basic real analysis and proof. So we will alternate between basic proof techniques and actual analysis. Okay, and actually the complex marathon is also, you can also seen as intro to proof. Like, the thing is, the more I started to do math and I teach math, it feels to me that the best way to teach proof is to simply not separate proof from actual math. You learn proof by doing proofs. And of course, every math intrinsically needs proof. Right? I'm not saying turning every calculus sequence into real analysis, but you got to draw the line somewhere, right? So some material has to be proved. Because the thing is, you can assume different things. Right? You can assume, say, the limit formulas and then prove a fundamental theorem of calculus. Right? So some sort of proof is definitely needed in every math. It's not a if, or it's not a binary question. It's a continuous spectrum. Like what kind of thing you can assume and then deduce the rest. Okay, the level of deduction, the starting point of deduction is the difference there. So if, let's say, ideally speaking, if you compare a quote-unquote proof-based calculus versus a quote-unquote non-proof-based calculus, the real distinction should be what percentage of stuff is assumed and the rest is deduced. Not something is proof-based, something is not proof-based. It feels like a binary choice, but to me this makes no sense. You know what I mean? So here, of course, for example, in this book by Brown and Churchill, there is a very clear line drawn here. So for results that require deeper foundation into real analysis, such as, compactness, they're simply bypassed. Okay? And other books, quote unquote, more rigorous books like L4, that's the famous Western classic, L4. It's very succinct, kind of like Baby Rudin, but for complex. And of course, you have the Russian classic, Markushevich. Right. Once you also have the Russian classic, the Markushevich, which really go down from the beginning, which assumes no real variable either. But certainly, there's still something is assumed. For example, certain facts from topology is assumed, like the Jordan curve theorem. It did not prove from scratch. Right, so the thing is, a difference between quote-unquote a proof-based math course and a non-proof-based math course is not binary. Okay, it shouldn't be binary, and I don't think it is binary anyway. It's just that the description is misleading. It's how much is assumed versus how much is proved. Right, how much is assumed and the rest is proved. It's like a beta distribution. It's a proportionality thing. And here, in this book that we're doing, some of the more foundational things like the completeness, which is really a topic in real analysis, is simply assumed without further discussion. And that's okay. You know what I'm trying to get to. So anyway, so hopefully this series, the link I just linked, the link I just put in chat is helpful for you. And let me know your feedback in the comment section. So yeah, there we go. Here we have the distance defined, and there's an important application of this, namely the equation of a circle, which we'll use quite frequently down the road, because we'll be doing integration over circles a lot. Circles. Okay, so example 1. First, we have minus 2 plus 2i taking modulus. This is the square root of minus 3 squared plus 2 squared, which is the square root of 13. Okay, minus 1 plus 4i modulus is the square root of 1 squared plus 4 squared equals the square root of 17. Right? So you can say the point minus 3 plus 2i is closer to the origin. We don't do PDF sharing on this channel here, but you can you can try it with other resources, but we don't do. I mean, I don't do PDF sharing on the because of copyright issue. I don't want the channel to get DMCA'd closer to the origin. Okay. Example number 2. Okay, I'm actually interested in optimal control. Perfect. Oh my goodness. I just started one optimal control, like an introduction, like what is the problem setup, what are the main results there. We'll definitely continue on optimal control if you're interested. I think I will alternate between PDEs and optimal control. Because right now we're kind of with, going strong with the stochastic series, and which means PDE stuff takes a little bit of a priority because I need heat equation really badly. But after that's done, we can come back to optimal control because we already did optimal control 1, and there are loose ends there. Yeah, your background is electrical engineering. Actually, Quinn, you're my target audience. I was just talking about this. So as I said, this is an applied math channel, so the audience are for general STEM audience who have advanced mathematics background. For example, have taken calculus, linear algebra, but has never taken, so to say, mathy math. Okay, so like proof-based math, and this is my main audience actually. So yeah, great. I think proofs is definitely useful. Actually, Queen, I apologize for the rest of the audience, just for another digression. Okay, so for example, a classic, I mean, not a, perhaps, yeah, it's a classic for sure. We can call it a classic. So Professor Evans from UCLA, also Dr. Payan, fellow YouTubers, PhD advisor, wrote a set of notes on optimal control, which we use for our first stream right here. This one. You can see it is very proof heavy, even though it did not require specific background in analysis. Okay, there's no specific background in analysis being called for, but the language, the style of exposition, and the notations are very similar to the ones used in analysis. Okay, and if you don't know any real analysis at all, I think you will struggle to read this set of notes. So last time we did chapter 1, most of chapter 1, and an overview of the rest, stated the two main results. One is the existence of bang-bang control and Pontryagin's maximum principle. Okay, so of course that leaves us with some loose end, rather big loose end. So I do intend to cover the whole thing, and which will include also a nice synergy with the stochastic series, because it also has stochastic control. Okay, so all of this require proof-based mathematics, because otherwise it's quite literally incomprehensible. Okay, and yeah, so that's optimal control theory. Optimal control theory is a final year undergraduate / beginning graduate level course, and at that level everything requires proofs. Oops, I think my channel is in danger because I showed copyrighted stuff. Okay, that's great. Looking forward. Awesome. Okay, so example number 2. Example number 2 says if Z0 is a complex number, R is a positive number, and R minus Z0 absolute value equals R. This is a circle. Circle with radius R, and center Z0. Okay, and here's the picture. Yeah, it just says the distance between Z and Z0 is R, so it's very straightforward. And later on we will parameterize, that is to say, describe any point. Okay, any point on the circle, any point Z on the circle using a parameter as a function. Okay, this is an equation but not a function. Okay, and now you have the example number 3. This is perhaps less trivial. So now let's consider describe. Okay, I wanted to describe the set. Example 3. Describe the set Z equals xy such that Z minus 4i plus Z plus 4i equals 10. So if you use standard method, like say if you substitute x and y in there and you do the derivations, it might be rather tedious because you have two square roots. Manipulating this can always be quite painful. But basically, if you look at the geometry on the other hand, it tells a rather clear story. So it says the distance between z and 4i and z between minus 4i add up to a constant. And by elementary geometry, this is an ellipse. If the distance the sum of the distance between 2 points, okay, actually, you know what, how do you describe this? If for an arbitrary point z, if the sum of the distance between z and point 1 and the distance between z and point 2 is a constant, then the trajectory of z must be an ellipse. Okay, I'm working on neuroscience, although I'm an engineering student, also interested in pure math, physics, philosophy, biology, etc. Okay, sure. Welcome to the community. Welcome to the community. We do some, although we don't spend, let's say, we don't spend an overwhelming amount of time doing pure mathematics. Okay, what we tend to do is, because as I said, the main audience of the channel are general STEM audience who want to know more math foundations. Okay, so that's why, for example, if I'm making a channel for pure mathematician or pure math major, I would simply not do the intro to proof because that's like assumed background. The assumed background for this channel is first 2 years of linear algebra and calculus. And that's the content that I make, that's the material that I make everyday quizzes from. So in case you're wondering what kind of intended background I have in mind, you can go to the community tab and see my daily quizzes. I'm not saying I will never cover those topics, but currently I certainly do not have time. And those are considered more or less things you should know before entering things like what we do on the channel, like mathematical statistics, PDE, that kind of thing. But currently speaking, perhaps the measure theory series and intro to proof theory is the closest to pure math, okay, without mentioning any specific actual concrete applications. So yeah, that's the set. That's the set. That's an ellipse. So this requires a little bit of a geometry knowledge from high school. Do you guys know in your home country? I'm just interested. Does your home country still teaches conic section in high school, or maybe you don't know? That's totally fine. In my country of residence, Canada, in Ontario in particular, they stopped teaching conic section in high school. I don't know why. I mean, this is another disappointment when it comes to high school mathematics. They stopped teaching classical Euclidean geometry, and now they even stopped teaching conic section. I don't know what they're doing. Conic sections are useful for calculus, not really here in Finland. No longer in. Oh, so also not taught in Finland, huh? So in classical Euclidean geometry, equation like this would be, because clearly the major semi-axis is in the y direction, because the focus is on the y direction, and that's where the major semi-axis lie. The focus 4i plus and minus 4 are the foci. Okay, wow. I guess that's the global trend then. We're not a singularity. They do it in China. Well, that's China. You know how China things are in China is like. Exams are super competitive. But yeah, plus or minus are foci. So this means the semi-major axis is the y-axis. Okay, so Fauci is 4, so the half focal length is 4. C is 4, usually denoted as C. So the equation for this ellipse is y squared plus a over a squared on x squared over b squared equals 1, where a squared equals b squared plus c squared. This is a fundamental relation in ellipse. You got, okay, great, awesome. How do you get 110% though? Is that there's a bonus? That's awesome. That's awesome. I'm glad that there are still places that teaches conic section. I don't know, like what's against conic section? Ellipse. Ellipse is needed in higher mathematics. Like the contours of Gaussian, multivariate Gaussian distribution. Contours of multivariate Gaussian distribution are ellipses. What's the matter with that? You know, if you study physics, ellipses are, this is the Kepler's law. Kepler's law says the planet moves in an ellipse. And of course, well, I guess they do teach parabola, so that's not really a fair critique. Parabola, they do teach parabola, quadratic function. But hyperbola is still, hyperbola gives the first introduction to asymptote. Even before calculus, you see an example of asymptote. How awesome is that? I don't know, what's the matter with them? Okay, anyway. Okay, I would just say I don't understand, okay? A squared equals still is, awesome. Awesome. Okay, so here, the A is this. A is 2 times 10. 2A is 10, okay? So this is not a proof, but merely a state of the result. So as a here A is a 5. A is 5, and as a result, B is the square root of 5 squared minus 4 squared, which is 3. So the equation is y squared over 25 plus x squared over 9 equals 1. So that's the set. Okay. Okay, anyway, keep going. I'll leave in 40 minutes. I have to leave in here. I will leave at 3 p.m. local time. Okay, and now finally we will do something related to analysis today, namely triangle inequality and a famous estimate. Because as my master supervisor told me, analysis is all about inequalities, whereas algebra is all about equalities. So far we've seen mostly equalities. And indeed, complex number is a great example in higher algebra, in abstract algebra. Okay, this is a great concrete example. And so far we've been doing mostly algebra, and now we start our first step towards analysis. That is, we're going to start doing inequalities. Okay, this is our journey towards analysis proper, called triangle inequality. So, triangle inequality. Triangle inequality is not hard to understand geometrically. So let's first draw the picture. This is, say, a complex number z1, and this is another complex number z2, and it just says the sum of z1 plus z2. I apologize if some of the audience already seen this stuff in the series Russian-style complex analysis, but I try to make this one self-contained, so there is some repetition. Okay. The triangle inequality says z1 plus z2 modulus is less than or equal to z1 modulus plus z2 modulus. Okay. The geometric meaning is rather evident, but let's look at its proof. Okay, let's look at its proof. And it is given as a guided exercise in Brown and Churchill. Actually, you know what? We can only do this after we've seen conjugate. And I don't think we have time to formally introduce conjugate. Okay, I apologize. So we will defer this. Okay, we will repay this debt. Okay, it's a huge debt because triangle inequality is definitely the number one inequality in complex analysis. We'll do that later. Okay, so the proof is delayed. The proof is given, is left as an exercise, as a guided exercise with a few steps. Delayed. Okay, so let's just take this as a useful result. Of course, it's very useful. We're just going to assume this, okay, and do other things with it, and see how triangle inequality can help us. Okay, so first of all, there is a corollary, equally useful, called the reverse triangle inequality. Reverse triangle inequality says the following. Triangle inequality gives us an upper bound of a sum, but sometimes you need a lower bound as well. Like, for example, sometimes you see a situation where you have a sum at the denominator and you want the modulus of the fraction to have an upper bound. The way to do that is to find a lower bound for the denominator, and this is where typically reverse triangle inequality becomes useful. So the reverse triangle inequality says z1 minus z2 modulus is greater or equal to z1 modulus minus z2 modulus absolute value. The reason we take absolute value is because we don't know which modulus, z1 modulus or z2 modulus is greater. So the right-hand side without the absolute value might be negative, in which case the estimate would be useless because the modulus on the left-hand side is always positive, it's always not negative. So here we put an absolute value sign. Okay. So how do you prove this? It's actually a great exercise, introduction to proof, because when it comes to direct proofs, so basically overall, when it comes to proof writing, there are two main strategies: direct proofs and indirect proofs. Direct proofs start from the premise and deduce forward, okay? Start from the premise and reach the conclusion. Whereas the indirect proof involves some sort of contradiction or contrapositive, right? So you negate the conclusion and try to derive something contradictory. So that's the two overall strategies. Each are important, each are equally important in my opinion, and you can't really just learn one without the other. But the thing is, for inequalities, there's usually very little premise to start from. Here, for example, there is no if, okay? If you write the full sentence for this statement, it would be for all z1, z2 in C, this inequality is true. But there's not a whole lot you can deduce from those premises. Okay, you know z1 and z2 and complex numbers, now what? Right? So in those situations where it seems that the hypothesis part of the statement is lacking, what we do is we would first try some scratch work, okay, and see what do we need to get to this result. So this is the common strategy called working backward. So scratch work. So to prove inequality, often you need scratch work by working backward. Okay, working backward means, okay, assume the conclusion, which is a cardinal sin, of course, in actual proof writing, but this is okay. This is scratch work. You can assume the conclusion and see whether it can be reduced to more obvious inequalities. You work backward to find the proof, and then in the actual proof writing, you write it forward. So this way, the logic is sound. You are not assuming the conclusion. But then, pedagogically speaking, it creates a barrier for the reader because it might look unclear to the reader how the proof is discovered. After all, it is scratch work. The scratch work is not shown. Here we are going to show the scratch work to see what's behind the scene. Okay, so let's work backwards. So let's assume this and see what happens. Z1 minus Z2 absolute value is, modulus greater or equal to the absolute value of Z1 modulus minus Z2 modulus. Okay, so, well, you have an absolute value less than something. So recall that if x absolute value is less than or equal to a, this means x is greater or equal to minus a, less than or equal to a. So this means that z1 absolute value minus z2 absolute value is less than or equal to z1 minus z2 absolute value, and is greater or equal to minus z1 minus z2 absolute value. Okay, so this is what you can get by assuming the conclusion. And now let's see. Don't worry about whether the logic is reversible now. Don't worry about it yet. Okay, and right now you just wanted to maybe unpack the conclusion into something that is more manageable. Okay, so we like to have mostly positive signs. So let's just call this, there are actually two inequalities going on. You have first inequality here and the second inequality. So let's look at them one by one. So this way things are, as I said, more manageable. So this implies 1. 1 can be rewritten as such. That is, z2 absolute value is less than or equal to z1 absolute value plus z1 minus z2 absolute value. I did this for no reason other than I hate negative signs. I do not like dealing with negative signs, so I rearrange the term so mostly you have positive sign. I can't do anything about the negative sign inside. Okay? Inside that modulus, I cannot do anything about that. So, but at least 1 implies this, and also 2. 2 says the following: z1 absolute value or z1 modulus is less than or equal to z2 modulus plus z1 minus z2 modulus. Okay. So are these true though? Are these two inequalities true, or can we prove these? Think about whether can we prove these. We'll try to use the triangle inequality because after all this is a corollary. The corollary should follow from the triangle inequality rather quickly. And here's the idea. Because we notice that z1 plus z1, actually here, perhaps the second is more obvious. So z2 plus z1 minus z2 is exactly z1. So the left-hand side, z1 absolute value can be rewritten as z2 plus z1 minus z2 quantity taking absolute value. And therefore you can just use triangle inequality to get z2 absolute value plus z1 minus z2 absolute value. And that's exactly 2. So 2 is proved. So this is a rather obvious inequality. Okay, and let's see if we can do the same for 1 because it looks very similar. But adding z1 with z1 minus z2 do not give you z2, like in the second case. But luckily, we can write the second term as z2 minus z1 absolute value. Changing the sign does not affect absolute value. So you can write it this way. So z2 absolute value this is equal to z1, okay, plus z2 minus z1, exactly like earlier, less than or equal to z1 absolute value plus z2 minus z1 absolute value, and this is of course z1 absolute value plus z1 minus z2 absolute value. So now 1 is proved. And now let's check whether the logic is reversible. Yeah, it is reversible. Every step you can go from, because going from 1 to this inequality is just rearranging the term. You can do it backward. Right? 2 is the same. You can also do 2 backward to recover this form. And the second line is also reversible to get the first line. So now you have discovered the proof. So start from here. The formal proof should start from here, starting with application of the triangle inequality, and then rewrite backward. That's the scratch work. Okay. So it is often said in epsilon delta style proof you need scratch work. What that really means is that epsilon delta proofs are inequalities, and inequality generally requires scratch work anyway. So that's how things are actually done behind the scene. Okay. Students often find proofs in analysis difficult because they aren't shown the scratch work. It's like going to the restaurant and you see the dish on your table, but you never see in the kitchen. Of course, the dish tastes amazing. You don't know how to make it yourself at home because you're never shown the kitchen. And here we're showing the kitchen. So let's start. Okay, let z1, z2 be complex numbers. Okay, so by triangle inequality, we have z1 absolute value equals z2 plus z1 minus z2 quantity absolute value less than or equal to z2 absolute value plus z1 minus z2 absolute value. Okay, so this is 1, and z2 absolute value is z1 plus z2 minus z1 quantity absolute value. This is less than or equal to z1 absolute value plus z2 minus z1 absolute value. And this is 2. So rearrange. One becomes the following. So z1 absolute value minus z2 absolute value less than or equal to z1 minus z2 absolute value. Okay, and 2 is the following, which says z1 absolute value minus z2 absolute value is greater or equal to minus z2 minus z1 absolute value. So combine into an inequality chain. So z1 absolute value minus z2 absolute value is less than or equal to z1 minus z2 absolute value, and is greater or equal to minus, and here let's do a sneaky change as well, sign swap inside the modulus, z1 minus z2 absolute value, and which is equivalent, or imply z1 minus z2 absolute value less than or equal to z1 minus z2 absolute value as needed. QED. Okay, so proving inequality often involves doing some scratch work. Okay, so that's the triangle inequality. Okay. So So often when you read books, and even when, say, the logic feels okay, you can follow the steps, okay, from one line to another, you might want to stop and reflect whether you're able to come up with such manipulation yourself. Because, for example, if this is a proof given in the text, I think following the deduction isn't particularly hard, but the question is, can you do the proof yourself, right? Whether is there any manipulation that feels unnatural? If there is something that you feel, okay, I can't seem to be able to come up with myself, or this manipulation seems rather ingenious, magical, you might want to write this in backward. You might want to write the actual proof in the book backward and see whether this fits the workflow of a scratch work. Okay, so that's what it's like in analysis, the state of affair in analysis. Okay. So yeah, when you present the final proof, you want to do it economically. You want to make it as clear as possible. But the thing is, perhaps paradoxically, in mathematics, clarity and good pedagogy are often not the same thing. Okay, anyway, so let's do some example. Example 1, it's a really simple example. Example 1, so let's say you have a z on a unit circle. Is on a unit circle. Z absolute value equals 1. So we want to estimate the following. Okay, we don't have time to do the estimate for polynomial today, but that's okay. So we'll do it next time. I do hope to get to a residual theorem by the end of August. Because we're doing a lot of PDEs, we'll be doing a lot of PDEs and transform stuff without complex variables. Things are awkward. So estimate absolute value of z minus 2. How do we do that? Well, first let's draw a picture. Whenever possible, draw a picture. Z absolute value equals 1. Is on the point on the unit circle. So what is this? What is z minus 2 absolute value? Well, that's the distance from z to 2. Can we get the estimate purely geometrically? This is 2. This is z. So we're looking for the distance between, I don't want to suggest this is a tangent point. Okay, so this is z, arbitrary point on the unit circle. Radius is 1. We want to find the longest distance between z and 2. Estimate. Estimate means both lower estimate and upper estimate. So it should be clear that here, this is the closest distance. And here, should be the longest distance. Furthest. Farthest. Guys, I'm not a native English speaker, but what is the difference between farthest and furthest? Or is there a difference? Solution. Okay? Solution. So here, let's use the triangle inequality first, because that seems to be the most obvious one. So this is less than or equal to z absolute value plus minus 2 absolute value. And z absolute value is given to be 1. So that's just 1 plus 2, which is 3. Exactly when you have the so to say the point on the polar opposite end that gives you the longest distance. And by the way, I forgot to mention, triangle inequality attains equality, okay, when not only z1 and z2 are parallel, but they need to be in the same direction as well. Okay, equality holds when z1 and z2 are in the same direction. Okay. And we will give an algebraic characterization next time when we discuss conjugates. Okay, but this is intuitive, right? Because right now it is not proved yet. But it should be clear that triangle inequality attains equality when not only z1 and z2 are parallel, but they're in the same direction. Because if they're in the opposite direction, the lengths will cancel. They won't add up. Okay, so that's the upper bound. And then you have z minus 2 absolute value. So we'll try to use the reverse triangle inequality. That will be the greater or equal to z absolute value minus 2 absolute value, and then take absolute value. So sometimes I say absolute value and modulus synonymously because they're the same notation. And I don't think there's anything wrong with that, because if z reduces to a if z reduces to a real number, let me actually put it here. So if z is x0, okay, the point on the real axis, then z modulus would actually be just the square root of x squared plus 0 squared. But that's exactly as x absolute value. So calling it modulus or absolute value, I think, is totally justified. And later on, for example, when we discuss complex series, sum of Zn, complex series, we can say absolute convergence. And by that, we of course means the sum of the modulus series, which is the sum of absolute value. So we're going to use absolute value anyway. Okay, so I will use modulus and absolute value interchangeably. There's no the risk of misunderstanding. Okay, so here just plug in the numbers. Z absolute value is 1. So 1 minus 2, taking absolute value. This is a good case to illustrate why do we need the absolute value in the reverse triangle inequality, because if we don't have the absolute value, this would just be minus 1. And the inequality would be meaningless, would be sort of useless. The modulus cannot be negative. So here you have a lower estimate, which is 1. And this happens at when z equals, okay, let's put the point when z equals minus 1, and this happens, equality happens when z equals 1. All right, so this is a simple example. And now let's look at another estimate. Example 2. So actually, before talking about example 2, let's do an extension. Okay, another corollary of the triangle inequality for finite terms. So it says for any n, z1 plus all the way to zn, absolute value is less than or equal to z1 absolute value plus all the way to zn absolute value. Okay, for any finite z. We're not discussing infinite yet because, as I said, this is pre-complex analysis. No infinity, okay, is involved here. In general, infinite sum is meaningless unless you assign the limit to it, assign some sort of meaning, usually in terms of limit to it. And we have not yet defined limit, so no discussion of infinite sum yet. Okay, so to prove this corollary, you would use the induction argument. We already did an induction proof earlier today. This is proving the binomial theorem. Here we're doing another induction. This one is arguably easier, definitely easier. So to do an induction, let's say we prove the inequality by an induction on n. Right? That's how you usually start with it. Declare the intention. We're going to prove it by induction. So now let's prove the base case. So the base case is interesting. Should you use base case as n equals 1 or n equals 2? Should you use base case as n equals 1 or n equals 2? Sometimes you need to change it halfway. Okay, proof writing in general is not a linear process. You write down the first line and then the second line without need to revise later. No, typically that's not what happened. Generally speaking, the best case scenario is that you have an idea of how to proceed a proof. You start writing it, right? And quite often you will have to change your wording, perhaps add a case, things like that. It's kind of like writing an article. You rarely just start from the beginning and go to the end and write until the end, like as if calculating an integral without a need to change anything afterward. Typically, that's not the case. Okay, so let's start with assuming that the base case is n equals 1. If there's any issue that comes up later, we will fix that. Some people said 2, right? Some people said 2 because it feels like n equals 1 is so dumb. There's nothing said. Right? So let's just say, because after all, this is true for all n. So this is indeed true, even though it's a very stupid case. This is obviously true. So we don't know if you need to include n equals 2 as an inductive case, but we will see, okay? So that's the base case. We might need to change it, okay? I'm just saying. And now let's do inductive step. Inductive step is as follows. So we start by assuming the induction hypothesis. So assume, basically for some, we should assume the idea is for, assume for some n equals k. This base case must be 2. You see, I think, Wendelin, I believe you were in my complex analysis Russian style stream the other day when we also mentioned this corollary. I just kind of brushed it aside. You can prove it using induction, and did not actually prove it myself. I should have done it because now we are dealing with this controversy. Should you start from n equals 1 or n equals 2? Okay, chat think it's 2. I wrote 1. We will see who's correct. Okay. Assume for some n equals k, the inequality holds. Okay. So now let's consider. This is the induction hypothesis. Then what? Then you have z1 plus all the way to zn plus zn plus 1 taking absolute value. And can I just say this is, like this. I'm using the triangle inequality here. This is triangle inequality. I did not quote anything other than this. I just use triangle inequality. And then use induction hypothesis. Oh, I should write k for some n, okay, just without need to write k, okay, just for some n. Guys, do you think this is correct? I think it's okay. I need your opinion. I think you can use base case n equals 1 or 2. So case 1, it is a tautology, so you have it for free. But the thing is, you also proved n equals 2 earlier as well. So regardless, you don't need to prove n equals 2, right? You don't need to prove n equals 2. So even if you just say when n equals 2, this is also proved. Which way do you think it's better, huh? Because as long as the triangle inequality is proved, here, as long as this step is justified, then we're good, right? This is an induction. Well, let me finish writing this. This is exactly what we needed, so therefore, as needed, therefore finish up by saying by the principle of induction, of mathematical induction. That's the standard wording. Induction proof, you finish that by saying by the principle of mathematical induction. If you use a strong induction, you say by principle of strong induction. Here we did not use strong induction. Okay, the inequality holds. Induction needs to be a separate live stream. Here we're just using it. Okay, so that's the proof. So I was thinking, as I said, case 2 cannot be deduced from case 1. So right now the proof is incomplete in my opinion. Yeah, great point. N equals 2 for some n, right? For some n. Here I'm just saying this is great point. This is interesting. Is this base case should be 1 or 2? So assuming that triangle inequality is already settled, okay? Okay, assuming there is nothing wrong with this, okay? Already we have no controversy over this. Then is this okay? So principle of mathematical induction says the following. Okay, so this is where we need to go back to the foundation. Principle of mathematical induction says the following. Actually, guys, let me quote the. Damn it! I have 3 minutes left. Oh, jeez, let me see if I can still find it. Okay, so here I have another textbook with the statement of PMI. PMI states the following, okay? This is an actual theorem that says, let PM be a statement about N. And N is a free variable. N in big N. So if you have the two things true, PMI1, PMI2, then blah blah blah. Okay, I'm just gonna finish up writing that. So it says the statement P1 is true. If for all I think Wendelin is correct. I think Wendelin is because PMI2 clearly says if for all integers m, for all positive integers m, we have P1, we have Pm implies Pm plus 1. So this is says Pm implies Pm plus 1. 3 minutes left, final countdown. It's a little bit, it's okay. At least I can finish this. Okay. Okay. I'll leave this as a homework to you guys to figure out. Did what I did? Is this valid? Okay. Because there was a horse problem that seems to suffer from the same problem. Okay, I'll put the horse problem next to it so you guys can have something to think about. For all positive integers n, Pn is true. So this is the formal statement of PMI. Wendelin's objection to my proof is that here in PMI2 you need for all m in n, Pm implies Pm plus 1, which includes P1 implies P2. Right? So Wendelin's objection to my writing, to my proof is that in PMI2 you also need P1 implies P2. But P1 is a tautology. Why is P1 implies P2 is unclear. So this will include P1 implies P2, right? But P1 here is a tautology. This is my P1. And P2 is a standalone thing. P2 is a standalone thing. So I guess you can say P1 implies P2 because P2 can be separately proved. Right? P2 is, well, we delayed it, but P2 can be proved on its own without referencing P1. I mean, after all, P1 is useless anyway. Right? So technically speaking, P1 do implies P2 because both of them are true. So true implies true. So there is nothing wrong with that. But here we are actually saved because of P2 is true. It is because of P2 is true we have P1 implies P2 being true, so everything still follows. So technically speaking, this is not wrong because I have not violated P1 implies P2. But there are situations where P2 is not true and the whole chain of deduction falls apart. Okay, so that's the famous horse example. So here this is a harmless step, but really to be more, so to say, to be more clear, it's not because of P1 implies P2, but rather P2 on its own is true, so that P1 implies P2 together is true. Okay, so even though there's no logical error committed here, it's still better to write base case as n equals 2. So that's my, so to say, summary of this situation. Let me just find the famous horse problem, which I think I've sent it to JC's discourse a few days earlier, because he was also covering induction. Raise your hand if you have heard about the horse problem, the horse proof. All horses have the same color. Oops. I just want to do the screenshot, okay? I don't want to show the whole book to get the channel demonetized. Induction. Yeah. So this is the exercise. No time for this exercise too now. So this is a horse problem. Let Pn denote the statement. For every set of n horses, all the horses in the set are in the same color. We quote unquote prove for all n in Z plus Pn by induction on n. Note that P1 is true. This is trivial. Right? Since for any set containing a single horse, all horses in that set have the same color, namely the color of that single horse. Next, let m be greater or equal to 1. Assume that Pm is true. For any set of m horses, all the horses in the set have the same color. That's Pm. You prove that Pm plus 1 is true. Let S be a set of m plus 1 horses, namely named x1, x2 all the way to xm plus 1. Now the horses, okay, so you can say the subset, right? Subset x1 all the way to xm are m horses, so by induction hypothesis, they have the same color. And now you consider another subset, x1, x3 all the way to xm plus 1. All the horses except x2 are a set of m horses. So by the inductive hypothesis, they have the same color too. So they all have the same color. Therefore, Pm plus 1 is true. What is wrong with this? Okay? So that's the food for thought here. Who is Hong Wang? I have no clue. Although n started at n equals, do we really need to debate that again? Okay. Anyway. So right now we have PMI2. PMI1 is true, right? I mean, this is tautology. This is always true. But my point is here, according to this general result, PMI, right, PMI2 in particular calls for P1 implies P2, P2 implies P3, P3 implies P4, and all of them in that pattern. But the problem is, do we have P1 implies P2 in our case? My answer is true, because P2 is a standalone inequality, the triangle inequality. Its proof is extended, but it can be proved without any reference to P1. Well, P1 is useless anyway. Right? So technically speaking, P1 implies P2 is not wrong, because you can say both the hypothesis is a tautology and the conclusion is the true statement. So true implies true is true. So P1 implies P2 is technically satisfied. So the alternative, would be, you have base cases, n equals 1 is true, and n equals 2. N equals 2, this is just the triangle inequality, the standard triangle inequality. Okay? And now you would assume for n greater or equal to 2, the inequality is true. And now this step would be changed to base case. I mean, it's still the triangle inequality, but perhaps mention this is base case n equals 2, and then induction hypothesis. Guys, do you think this is better? This way we avoid the issue of P1, I mean, not the issue, but really it's, I don't know how to put this. How do you describe this sort of statement? P1 implies P2, whereas P1, the proof of P2 does not involve P1, but rather just the fact that they're both true. Okay, I think that's a good place for me to stop today. I really need to go. I had a lot of fun today. I did not expect this seemingly trivial induction proof would give me issues. Okay, always not to underestimate, uh, you know, basic math. Yeah, compare with my original proof, that is without the green stuff, with the proof for horse. Where did horse proof go wrong? Do you have P1 implies P2 in this case? Obviously you don't, right? Obviously you don't have P1 implies P2 here. Because in that case, the two sets, there's no x3. When m is 1, there is no x3. So therefore, this proof hinges on the fact that there is intersection of these two sets. x1 all the way to xm and x1, x3 all the way to xm have non-empty intersection. But if m is 1, m plus 1 is 2, then you can just say, oh, you only have two subsets, two non-empty subsets, two non-empty singleton subsets. Say this is x1 and x2. Of course, these are singleton. X1 have the same color, x2 have the same color, but they do not. You cannot merge them together. Right here, you have this merge argument. You cannot merge them together. So P1 implies P2 is definitely false here. Okay, so that's it. Okay, that's it. So we'll leave this for you guys to think about, and whether my original proof without the green writing is valid. Okay, so that's it for today. Thank you very much, guys, for joining the stream, and I'll see you next time. Bye. See you tomorrow, actually. We'll do some stochastic differential